All right, so I'm here to talk about Zephyr I3C. So what I'll be getting into today is I'll just be going over a brief I3C overview. As I imagine most people here aren't familiar with I3C, then I'll talk a bit about how I3C is used within Zephyr. And I'll talk about how the future of I3C within Zephyr. All right, so I'll begin with just a brief overview. So first thing I want to get out of the way is just sort of the new terminologies with I3C and I2C. So there were terms master and slave, so now the terms are controller and target, and this is now written in the specification. And also I2C did get a specification update for these new terminologies as well. All right, so I3C, it's not a typo, that is a 3. So there is some differences. So this does use sort of the same SDA, SCL pins as I2C, but there are a little bit of differences here. Probably the biggest thing that you'll notice is the bus speed. So the bus speed in I2C typically goes up to 1 megahertz. There are faster modes as well, but I3C can get up to 12.5 megahertz for the standard data rate. There's even high data rate modes, such as double data rate, which is the most common, which is about 25 megahertz. And there's even a ternary mode, which is about 33 megahertz as well. So for I2C, typically the pull-up resistors are external. So for I3C, typically they're built into the pad of the controller. So physical signaling, along with the higher speed that I3C uses, this does require it to be in sort of a push-pull mode when possible. And addressing, so I2C has static addressing. I3C, the addresses are a bit more dynamic, where they are assigned upon initialization. So interrupts, like for, let's say you have a sensor, an accelerometer, typically you have like a data ready pin, for example. And that does require additional I/O on your processor. So for I3C, there's something called N-band interrupts, where basically the interrupt sort of happens in line on the data lines that a device can give. So I3C can also support hot joining as well. So device can be plugged in or powered off and get assigned its address. There's also even common command codes that is more of a standard way of communicating with devices. So I want to talk about the terminology as well, because I know when I try and teach people I3C, some people get a little confused on the terminology. So there's 3 terms for a controller. There's primary controller, secondary controller, and active controller. So primary controller is this is the I3C controller that upon power on, it acts as the authority and configures all the target devices. So in the initial state, this is the first active controller. So a secondary controller, these typically act as targets upon their first power on. But these can also accept the controller role from any active controller. And once it becomes a new active controller, it can then pass it back to the previous active controller or onto any other controller-capable device on the bus. So an active controller, this can only be one on the bus at a time, but this is the I3C device that presently has control of the I3C bus. And also there are devices that are just target-onlys. So this is maybe what you're all familiar with. It just can either respond to common or individual commands from a controller. So there's even more terminologies here with addressing. So we have dynamic addresses, which these are the addresses that are assigned during initialization for who to respond to what. And typically priority is encoded with these addresses as well. So, and there are also 2 optional addresses that devices may support. A device can have a static address. This is basically similar to what you'll see for an I2C device. Some devices may also support I2C as well, and they will typically use that static address for their I2C mode. There's also group addresses, which is came with the I3C version 1.1 specification. So basically, this is a separate address from dynamic address where basically a controller can assign a group address to like a group of sensors or a group of cameras, for example. So that way messages can be written all at one time to multiple devices. So the bus is pretty much very similar to how you see I2C. It is also backwards compatible with I2C targets, so an I2C target can exist on an I3C bus. Right, so in I3C, there are common command codes as well. So these are a standardized set of commands. So some are mandatory, some are conditional, some are optional. A lot of times if you read the data sheet of like your sensor that you're working with, they'll typically have a table listed of the supported common command codes. And they can also be like broadcasted to all devices on the bus, and some can also be directed to a single device as well. And also, every I3C device should have a provisional ID. So this is the uniquely identifiable ID that is used to identify the device during address assignment. And there is sort of a bit mask for how things are set within it that define like the manufacturer ID, which MIPI will assign for it. There's even more of the vendor fixed values that define like the part ID, the instance ID, which sometimes maybe come from pin strapping of the device as well. All right, so in-band interrupts. This is probably the feature most people see with I3C. So there are 3 types of IBIs, but probably the most common one when people just say IBIs is the target interrupt request. So let's say if I have an accelerometer connected and basically an event happens, like I have accelerometer data ready, for example. The target will then broadcast its dynamic address on the bus, and, along with possibly a mandatory data byte and even a payload, which could describe what kind of event is happening. So when that happens, the controller receives that IBI, and it should handle it accordingly, which I'll talk in the future slides. So there's even hot joining as well, where it broadcasts the address to, which is a reserved address. Basically that says, hey, a device either powered on or is plugged in, I need an address. It's up to the active controller to then assign it a dynamic address. And also controller handoffs also happen in the in-band interrupts, where basically a secondary controller is requesting to become the active controller. It's still possible for an active controller to refuse this handoff as well. So there has to be some sort of state for making sure that you want to retry later or figure out what you should do in that case. So I3C also has another difference from I2C is that the 9th data bit. So with I2C, that 9th data bit was typically an ACK and NAC for reads, it was used to tell the target when the read has ended, and for writes, it was just used for an acknowledgement of transfer. So with I3C, this is called the T bit, which stands for a transitional bit. So for reads, this gives the target control of when the transmission ends. So the target has control of when it will stop transmitting data. And that's called the end of data bit. So it can either say like not end of data and it will continue transmitting data, or just says end of data, and that tells the controller, okay, this is the end of the packet. It's still possible for a controller to like abort the transfer in the middle of a transaction if the target keeps sending it more data and more data than like a buffer could allow. But for writes, that T bit is used as a parity bit. All right, so now I'll talk a bit about how the Zephyr is typically used with I3C. So there are currently a lot of headers within there that sort of define the APIs and helpers within there. So there's like a common command code helpers that defined all the standard common command code macros and all the defines that come with it. There's even some device tree specific macros for I3C, which I'll get into later. There's even address related helpers, which help with assigning it, looking up what free addresses are available to assign to an I3C device. There's even I3C target device support as well. So I3C and device tree, this is kind of a little confusing because it's quite different than how I2C. So typically with I2C devices, you have the reg, which just shows off your static address. But for I3C, this is quite a bit more. So the first element is still the static address if it has one. Of course, static address is optional, so if it doesn't have a static address, then those are to be 0. And the second element is just the upper bit, is the upper 16-bit of the 48-bit PID. So you'll typically find that within your data sheet of the part that you're working with. And the third element is just the lower 32-bit of this provisional ID. And also, I2C devices need to be defined in, let's say, some of a unique way as well. So just like before, the first entry of the static address is, the first reg entry is just the static address of the device. And the second element is always 0. There's a bit under the hood magic with the macros to determine that this is an I2C device by knowing that second element is 0. And the third element is actually something new with I3C for compatibility mode called the legacy virtual register. So basically, when you're in this compatibility mode, this does sort of affect sort of the timing of certain of when you toggle the data lines. And I don't have time to get into the details of all that, but basically, you need to find this, and this does sort of change how your I3C control will be configured. So basically, the upper 3 bits define if it has a spike filter and if it is max SCL clock frequency tolerant. And the 4th bit just sort of defines if it supports fast mode plus or if it's just a fast mode only device as well. So it knows. So this is sort of used when it's broadcasted out to other devices to know what speed it can support. Okay, so all I3C devices have this descriptor struct within it. So basically, under the hood, this gets put into a singly linked list, and this basically is contained within the driver data of the controller. So basically, this does contain the device pointer for the device itself, along with the bus pointer as well. And this does contain all the required and optional standard I3C data within it. So it has the constant PID, the constant static address. You can even, in a device tree, you can even request an initial dynamic address, and there is some priority encoded with that, so you may want to think about it a bit, as well as the current dynamic address, group address, as well as standard control registers within it as well. Okay, so as I showed earlier, the struct I3C device does also contain the struct I3C device descriptor is looked up through the I3C device find. So when you want to retrieve that pointer to the device struct, all the I3C API has this I3C device find. So you pass the bus device along with the device ID. And this device ID is just the PID, which you read from the device tree with the macro below. So you read that ID, you then pass it into this API here, and you'll get, well, hopefully it's found. Otherwise, you'll get a null pointer of the I3C device descriptor. And once you have that device descriptor, unlike I2C API, the bus stub is not needed for private transfers because, well, it's already in that, it's kind of redundant. You've already got in that device descriptor. So you pass in that device descriptor is used instead of just the bus contained with it in it. So however, some of the I3C APIs that are broadcasted still use the struct device pointer. So if you're broadcasting the common command code, for example, you still use the same bus. Or if you're doing the more specific common command code, dynamic address assignment, which has a lot of special stuff around it, then you just pass the same bus pointer with that as well. So, and for target interrupt request, so if I'm like working on an accelerometer or sensor, I need to have some way of basically getting back the sort of having a way to be called into for, like, let's say accelerometer data ready or gyroscope data ready, for example. So when the controller receives an IBI TIR for a target, it will then enqueue the request into a work queue. And so it is up to the device driver for the target to set up its own function pointer. So it should get its own device struct and then write to that IBI callback function, which will then be called back, for example, like, okay, I got my gyroscope data is ready, go out and call the function to then go out and read the registers for gyroscope. So, and there is target support as well. So if you're acting as a target and you want to issue like a hot join request, a TIR, or a controller handoff, then that is the IBI raise function, and there's a struct where you need to find the IBI type, hot join, controller handoff, or the target interrupt request as well. So target interrupt request can also come with a payload as well that is sent out to the controller if it accepts the IBI. So there is also backwards compatibility with I2C. So there was a lot of debate on how to implement this, and it is kind of a little silly, but it's kind of the only way to get it to work is basically the I2C driver is just nested within the I3C driver API. And this does allow for all existing I2C APIs to be used as is. So that means all the entry GPIO expanders, entry sensors, or external ADCs can be used as is with just an I3C device controller. All right, so there's even sort of a helper function in here. So when a primary controller has finished initializing, there is an I3C bus in it within I3C common.c, and this just sort of handles sort of the common code between each driver so we're not duplicating code in multiple places. So basically, this will reset all the devices on the bus. There's a common command to do that, as well as resetting the dynamic addresses for everything so we get everything back to a known state, as well as disabling events. So basically, events are just IBI. So this basically makes sure that, okay, I'm about to begin initialization. I want to make sure no one tries to issue IBIs, tells all devices to be quiet because I don't want someone trying to interrupt me while I'm trying to perform initialization. So some devices will have static addresses. So there is sort of another common command code for assigning dynamic addresses from the static address. Well, basically, hey, I want static address. I want to have who has static address like 64 to have dynamic address 32, for example. And basically, it checks through its own list. Okay, did every device has a static address get assigned? Okay. Then it moves on to the next stage, which basically enters dynamic address mode. So this is something that's required by all devices. So even devices that do not have static address, well, basically this sends out a broadcast saying, hey, anyone need a dynamic address? If it gets an ACK, then it's up to the target to then broadcast its BCR, DCR, and PID. And there is some arbitration within there as well. Well, basically, the one who has like the smallest number of all those combined will win first and get the dynamic address. And then it broadcasts the dynamic address again. Okay, anyone else need an address? Okay, someone else tries to win arbitration. Okay, assign another address. Okay, broadcast again. Oh, I got an ACK. That means no one else is there. Okay, and so then once that's done, it then retrieves all the device info for devices. So this includes like the max read length, the max write length, for example, of a device. Also retrieves the BCR, the DCR, which I'll get more into later, as well as PIDs, and there's even some additional data within there as well. Once that's done, it should then re-enable all I3C events. So people can now talk now. The controller's finished with initializing the bus. All right, so I'm going to talk a bit about the bus characteristics register. So this is something required by all devices. So when this is read by the controller, this sort of lets the controller know how it will act on the bus and what it can do. So the two most significant bits define sort of the role it can do. It will say, hey, I'm only a target, or it can also be, hey, I'm a target, but I'm also controller capable. I may ask for, control of the bus later, possibly. There's even an advanced capabilities bit. This will define if it supports, like, let's say, high data rate modes, for example, multiple group addresses. There's quite a lot within there that they just add within the new version. There's also IBI payload. This defines if it is capable of issuing an IBI. There's even another bit that will define if the IBI will come with a payload that will contain data with that as well. And also, some devices may have a max data speed limit. So if there is a limitation, it's then up to the controller to go out and read what's your max speed, for example, which can be 10 megahertz, 8, 4, or 2 megahertz. And it's up to the controller to then make note of that when it's addressing it. So for I3C device drivers, it is to contain with its provisional ID, which is read with the I3C specific device tree macros, and also contain the bus and the pointer to its own device descriptor, because you want to read it once, and then you use that for doing the I3C transfers. So when it's during the initialization functions of these sensors, for example, it's up to the device to basically find its I3C device descriptor at runtime. So you have the bus, the device ID you read in that should be in your device config. And then you should go get the I3C device descriptor, which then should be stored within the device data. All right, so the extra I in I3C should not stand for inaccessible, but there is currently, like, let's say, not too many driver support, but there are like new devices coming out that do support I3C. So I believe in XP, the RT600 and RT500s do already have I3C support, and this is within XP. There's even the more, like, let's say, design fab houses like Synopsys and Cadence, which you'll typically use with FPGAs, that do have I3C support. There was just one actually published last week for the NPCXs, which is currently under review. Synopsys DesignWare I3C, there's currently like 3 pull requests to get that reviewed and merged in. Hopefully that will get merged in someday. And even STM32H5s also is a newer family of SoCs that does have I3C within it. There's just no Zephyr driver yet. But from what I see on Discord, there is someone trying to work on that right now, and hopefully there'll be a PR soon. And I was sort of going through the list a few days ago. I believe there is also an NRF controller that is sort of experimental that will have I3C support. So for device support, most of these are sensors. So like accelerometers, gyroscopes. There's even some current Zephyr drivers that do exist that, let's say, that do support I3C, but they don't have that interface implemented. They only have SPI implemented, for example. So basically, when someone needs it, someone could basically implement I3C support on like a BMI 323, for example. All right. So now a bit about like what could come for I3C. And I know the specification, if you find it, like is 600, 700 pages about, or is it 400? There isn't everything implemented within I3C within Zephyr yet, and not everyone has quite used everything yet, but I'm sure that will come soon. So shell support. This is probably the most easiest one to get done. I do have an open PR to basically give shell commands for I3C. This is very useful for if you're developing like a controller, you want to test something, or I have like, let's say, a new device that I'm trying to bring up. I want to, like, let's say, do arbitrary reads and writes of registers, or I want to just send a common command code, for example, to read some arbitrary value within it. There's also high data rate modes for that aren't quite fully supported yet. So there is high data rate, double data rate is probably the most common high data rate mode that you'll see. And this does, let's say, have a sort of a standard format that does contain like a preamble, a parity within it, addresses, and even a CRC within it that's defined within a certain way. So basically, there could be, there are to be macros in the future to help assist with this, to just get the commonality between all devices. So, and some devices do require the firmware to be responsible for the CRC, where it has to like read the payload, calculate the CRC at runtime. But I believe other I3C controllers do that within hardware for you. But this could also be implemented within the Zephyr CRC subsystem. It's actually the same CRC5 that USB uses as well. All right, so I know I did mention earlier that there is a controller handoff within IBI, but currently no one implements it. And there's even, let's say, some additional work to get that working as well. As if I'm a secondary controller and the primary controller just assigned everyone the address, how does the secondary controller know what was out there, who got what address? The secondary controller should not be changing addresses to something it knows. So basically, this would require modifying some of the Zephyr common code to send out a common command code called define targets at the end of bus initialization or when someone is hot joining the bus. And basically what this would do is inform all the secondary controllers of the device on the bus with their current dynamic address, the PID, the BCR, and DCR. And it would be up to the secondary controller to match the PID, like, oh, this is that sensor I want to talk to. It has that PID. This is its dynamic address. That's what I use to talk with it. And it's also used to define I2C devices on the bus as well, along with its legacy virtual register within it. Okay, so I3C also supports something interesting as well, called timing control. So basically, if I have a gyroscope or an accelerometer, it's kind of important to know, like for some algorithms, to know the timestamp of when that occurred. And previously, some people would use like the rising edge of like a data ready pin to know when that happens. But well, if you're using IBIs, then you don't have that pin. And plus, if it's an IBI, you don't know when that device could win arbitration of the bus, or the bus may be busy, and that IBI comes out much later than the actual sensor time. So basically what timing control is basically it's a way of broadcasting the timestamp of when that time occurred. So all devices should have its own internal counter, basically, as well as the controller has its own clock frequency, which is used to correlate the two times with one another. So basically, the controller needs to understand, okay, what's the clock frequency it uses for this counter, sets the get X time, and that also would enable the timing control, and that gets its clock frequency, and then uses that to correlate the sample times to its own clock frequency in order to calculate the actual sample time of the event. Right, so I3C and I2C routing MUX devices. Currently, there are a few entry I2C MUXes, and it is a little, let's say, difficult to get that working on with the device tree macros. There are, let's say, some ugly hacks just to make it just work. I've had to do it myself. I think I've heard other people had to do it as well. This also does present an issue down the road about how basically a MUX and even routing devices could have its own set of dynamic addresses. So basically it needs to take into account like, okay, I need to assign the specific dynamic addresses are free on this route versus that route. So currently device tree macros do not read past the first level of devices. Can be a little bit problematic since I3C and I2C devices do get under children of existing devices. All right, so about that get device info as well. So basically, there's sort of that common I3C get device info, which will basically go through and call all the CCC functions and even write to the device descriptor for you of all those common codes. So basically, there is a bit more that needs to be done, especially with bringing in like high data rate modes, for example. So basically what needs to happen is that it needs to do a bit more, like read this BCR bit. If some of these bits are set, that means, there's more information that needs to be read, such as getting the max data speed limit, also its advanced capabilities as well. So this was something kind of fun I just added recently that I did see get published a few years ago. There was actually a USB I3C device class, which is kind of new. Although I don't know when or if this would even come to Zephyr, because I don't know if there would be a need for it anytime soon. I don't even know if there's host drivers out there yet. But basically, this does sort of allow an interface to expose and configure the I3C function within a USB device. And it was kind of cute what they did in the specification, where basically all USB devices have, let's just say, a byte that defines what class it is, like I'm a CDC class, I'm a HID class. And what they did for the I3C class, they just did the device as 3C as the byte identifier, which was available. It was kind of cute. Okay, questions?
Thanks for this, Ryan. When you get an IBI and it goes into a work queue, or is there only one work queue for this, or just how would you do prioritization?
It is in that system work queue. I can't quite recall at this moment how that is prioritized. I think, if I recall correctly, I think there is sort of a K config within there, but I think I have to get back to you on that. Mm-hmm.
So it seems like I3C in general is a bit of a step up in complexity from I2C from like a protocol level.
Yeah.
And I2C devices, at least simple ones like temperature sensors, ultra low power, they're basically not there if you're not using them. Are there like power implications of like the counters on the target devices and the time conversions and everything else that the controller is doing?
There shouldn't be too much power constraints, and even then, I3C for the amount of joules per bit is a lot lower than I2C, for example, with even the push-pull of it as well. But yeah, it typically, I3C is going to be lower power in the amount of bits you're transmitting, for example. So and even when you're doing like high data rate modes, it's even less power because you're less power per bit as well. But about that timing clock, some devices can be, let's say, offline capable. I didn't talk about that in the BCR, where a device can, let's say, power down and may not always respond to commands, but that just sort of lets it know through that BCR register as well. Does that answer your question? Or?
Yeah. Just out of curiosity, if it can't always respond to commands, how do you know when it can?
Well, that should be understood by the controller or the device driver when it can. So,
So just a question on the hot join support. So I guess, in Zephyr we don't really have any hot plugging mechanism, right? Device trees all at compile time. Is the idea for that for like power savings, since the device can, I guess, be depowered and then hot join the bus at a later date? And then if it can, is there a mechanism for a bus to, or for a device to power off and leave the bus temporarily, I guess, so it can kind of join and then leave with I3C?
Yeah, that is sort of follows along with the off-join compatibility, but with the off-join compatibility, it should be expected that a device will retain its dynamic address as well. Otherwise, they'll have to go through the whole initialization process again to get a new address.
Thank you. Do you foresee I3C becoming a replacement across the board for I2C, or do you think these two standards are going to continue on in parallel for the foreseeable future, especially for less complex or lower throughput devices?
Well, I can't really predict the future decades on, but I know more complex devices are moving to I3C as things want to get smaller and lower power. I3C is going to be the better option versus like, SPI, which can require a lot more pins. It does have, backwards compatibility as well with I2C, so any future devices that come out could easily live on the same bus as well.
Hi, Ryan. Yeah, thank you for reviewing my MUX patches on the on the upstream. I just want to ask, I've worked with a lot of I3C devices, and I've noticed that a lot of them kind of don't support the vast majority of like the spec, in the sense that they seem to me like they're just using existing I2C capabilities, but they just added like the higher speed and they just called it a day. No dynamic address assignment, no hot join, interrupt support, and stuff like that. I'm wondering if you've seen that before, and if you think that we should push manufacturers and like the groups, for example, like the DDR manufacturers, which is JEDEC, to like have like the whole spec supported, and if that's like an ongoing thing that we're working on, if you've encountered.
Yeah, I know that as you, like, let's say reconfigure those IPs, like the die size can be a little bit bigger for some devices and even power constraints as well. But I mean, it's really up to the implementer on if they really need like double data rate, because some may just be like a temperature sensor or gyroscope. You're just reading a few bytes at a time, for example. But yeah, I mean, some devices do see even I3C versus I2C, like power constraints, and even a higher speed is even like a benefit as well. But as far as getting manufacturers to support all the specification, even then, some of these IP vendors that will make the sort of the RTL don't even support the full configuration of the specification either. But I have seen as time moves on, they do get more of the specification implemented. So those people who are like creating those devices have those options to add those in.
Thank you.
I just wanted to get your opinion on the coexistence of I2C and I3C devices on the same bus. Would you think that's a good idea? Basically, if it's a safe idea, because theoretically the concept is great, but you rely on that 15 nanosecond deglitch filter that I2C devices should implement if they are compliant to the spec, which, as we all know, may or may not happen. It's up to the vendor to actually make sure it complies to that spec. So, have you seen, or do you think there might be interoperability issues in that sense, so it would be dangerous to combine devices on the bus?
Yeah, that is actually written to the specification too. There's different like mixed modes and like even a pure mode as well. Basically, you get sort of limitations on the bus as well. Like there's mixed fast mode and mixed slow mode, like if the device doesn't have that glitch filter, for example. And even then, like if you're in a mixed mode, you can't do some of these like high data rate modes, for example. Like you need to have only I3C devices on the bus, if I'm recalling that correctly as well.
Thank you.
So what would you say the current market share of peripherals using I2C is? And is it a little bit of a chicken and an egg of microcontrollers being hesitant to fully embrace that, and then the peripherals also being hesitant to embrace it because you don't have micros embracing it? Or is it both kind of across industry a push towards adopting I3C?
It is kind of a push, but it is going to take time. I mean, a lot of controllers already have I2C, for example, and if you just replace that with an I3C, you still retain your I2C support. So you're not like losing anything there as well, even for controllers as well. You can still maintain the let's say for legacy controllers that support I2C just on the same pin with the same controller as well.
Thank you.
What's the best way to get started in Zephyr? So what's the best board and the best sensor to just plug and play and try it out?
For I3C, for off the shelf, I know there are the RT600 as well, but I know a lot of people love STMs for example. So there's that H5, which I think they do have some dev kits you can order. But like I said earlier, there's no driver yet. But I believe someone is going to be publishing that soon based on where, because he is saying he is working on Discord. But as far as sensors, there is sort of that list as well. I think if you just Google I3C Cafe, for example, there's someone who has a blog post about current I3C devices as well.
Yeah, we hit time, so any last questions? If not, thank you, Ryan.
All right, thank you all.
Test.
test. Yeah, sweet. All right, I think we'll get started. So, welcome everyone to Device Power Management. My name is Jordan Yates. I'm a maintainer of the LoRaWAN and the Seamless Neural Network subsystems, and also a collaborator on the power management stuff, which is more relevant for this talk. Just got a couple of quick disclaimers to put away. You might have noticed that the company name on the schedule differs from what was on the slides. So I'm no longer a CSIRO employee. I'm presenting this work with the permission of the CSIRO in a personal capacity, and all work here was funded by the CSIRO. And I'm very appreciative that they gave their permission for me to still present this. Just quickly, for those who may not be aware, just some quick abbreviations. So I'll be using. So A is like amperes, so current, milliamps, microamps. The little tilde is approximately PM, power management subsystem. And power consumption is like, I use power consumption as current more so than microwatts, just because it's easier for me. So why do we care about power consumption? Well, the power you use needs to come from somewhere. For mains powered devices, at least based on Australian electricity, 1 amp continuously over a year is about $9 Australian, so $6 US. It's not a huge amount, it's not nothing. Maybe it matters, maybe it doesn't. But for battery powered devices, it's basically the most critical part of the whole, well, one of the most critical parts of the whole design. If you can reduce your power consumption, you can have smaller batteries. If your battery stays the same, you need to swap the battery less, or you can have a smaller solar panel or something. A lot of applications just have inherent size and weight restrictions. If anyone attended my talk yesterday with the cattle ear tag, there is just a certain size you cannot go beyond. Otherwise, it's an animal ethics problem. And reducing the power consumption makes it much easier to hit that energy neutral state of the amount of energy I'm using is less than or equal to the amount of energy that's coming in. So your device will operate indefinitely versus your device will run for 2 weeks. So what sort of battery lifetimes are we talking about? I've just taken a standard off-the-shelf coin cell battery. It is a small coin cell battery, but for say a 650 milliamp hour capacity, the difference between hitting 1 milliamp average current consumption, which might be 27 days, versus 10 microamps, where it's 7 years, like in an absolute sense, the difference between 1 milliamp and 10 microamps may not be a lot, but in terms of lifetime, it can be a really big, have a really big impact. So this is a bit of a journey. So what hardware are we looking at for this? So inside of the CSIRO, we had a whole range of kind of general purpose development platforms. And then for different projects, we would design custom hardware. But this is one of the general platforms. So it's a Nordic-based microcontroller. It has multiple radios. It has Bluetooth from the SoC. It's got a LoRa modem. It's got a U-Box GPS modem. It's got a whole range of sensors, accelerometers, IMUs, environmental, light. It's got a audio codec for microphones. I don't think it has speaker out. It's got your battery management stuff. It's got an external SD card. It's got onboard flash. Like, it's got a lot. So when you're designing something like this, you sort of, like, when you go to design a piece of hardware, you have an overarching goal of the thing you want it to talk LoRaWAN, you want to measure temperature or whatever. But you also have sort of probably a budget of some description for power consumption. So when you're first looking at this, you're like, okay, well, what parts do I want to put down? And what am I likely to actually hit in terms of power consumption? So for us, the way we normally do this is we essentially, for each thing we're doing, like for each functional block we want, we basically scan through the options, find the part number which works the best for us. And then there's essentially two numbers here that matter. So one is the amount of power that a device will use when you apply power to it and you do nothing. That here is what I've called the boot power consumption. And then there's the minimum power consumption. So if you configure it in the best way you can, what power consumption will you hit then? And for some of these sensors, they're the same number. They boot up into their lowest power mode. But for others, that's very much not the case. So GPS modems, for example, are sort of notorious for you turn them on and they start running. 30 milliamps versus 15 microamps, that's a lot, right? So, but if you're looking for what's the theoretical minimum power consumption of your hardware, it's the minimum you're looking at. So I've got a list of these parts here, continued here, and total. Now, you may remember from the start of the title of the presentation, Journey to 5 microamps, and then you look at that total minimum there, 300 microamps. Well, we're sort of already in trouble, right? Like, how are we going to hit 5 microamps with what's going on there? And just like the boot current as well is just ridiculous. That's never going to work. But no one says that all of your parts always need to be powered, right? For parts which just draw too much power, even in their absolute lowest power state, you can just cut the power to them. And sure, that adds a part, and that part itself draws current, but that's like 0.02 microamps. So you add 0.02 microamps, you remove 100 microamps, milliamps, whatever it happens to be. Now, it's obviously not free. There's a cost, not a physical cost, an actual cost to the hardware component itself. There's also a software cost, right? Like your software is now more complex. And cutting the power also adds, there's a hardware cost as well in terms of complexity, right? Like there's more things to be aware of. Like if you cut the power, if you cut the voltage on the power pin, but your communication bus is still powered, well, it's quite likely that power actually just flows back through those communication pins and then sort of half powers the peripheral, and then it's real annoying. So there's more stuff to be aware of. It can mean you need stuff like essentially switches on the communication lines as well. So how does this work on our development platform? So essentially we throw in PowerPoint, we throw in what the minimum power is for all these peripherals, and then we sort of just partition those off based on what is always low power enough to just be always powered, and also like what things are likely to be used together, right? Now, you could put all of the high power stuff on off a single switch, and that would save you part numbers and stuff. But if you put your micro SD card and your GPS modem on the same switch, every time you want to write to your SD card, you've got to turn on your GPS modem, takes half a second to boot, 30 milliamps while it's running. So you need to be like cognizant of your application, what's likely to be turning on at what times, and sort of split your power, in a way that makes sense for that. I guess this really comes back to the fact that like power management is inherently a hardware thing. You can't just write really good software and suddenly get really good power consumption. It is a holistic thing of hardware plus software. So we've made our hardware, we've done our power domains. Now we get to Zephyr. So, okay, we've done our device tree, blah, blah, blah. We boot up upstream Zephyr, we run samples hello world, flash it, and then how much power does it draw from the battery connector? Just as a side note, I guess, a lot of these graphs are from measured using an ODI arc. I would not have included this like 3 weeks ago, but they've really updated their licensing to be much more user-friendly, so I'm happy to give them a plug now. So we flash this application and we hit 2 milliamps. Now, that's much better than what you might have expected from the 32 milliamps brute current, but the power domain drivers are not enabled, and our power domains have a default off, so you get a bit better performance than what you would otherwise expect. If suddenly you just modify hello world to only, like just to add in the power domain drivers, well, suddenly we start, can you guys read the numbers on the power or not? Sort of? No? Okay. So essentially that's just, the shaded area is just the time period over which we're measuring, and the average power consumption for that is 33 microamps. And on the previous one, it was 1.94 milliamps. So 1.94, turn on power domains, 33 milliamps. And that roughly matches our calculated baseline from the first few slides. And in that case, we know, okay, sweet, it's what we expect. There's probably no major hardware problems on the board. No one's thrown a 10 ohm resistor across our voltage line or whatever. So we've got our baseline. It's obviously not where we want to be. So what do we do next? Yeah, so I guess a bit about Zephyr device power management in general. Devices always default to the active state. Now, active state typically means the device is running, it's ready to run samples, to retrieve samples from. Suspended is generally just a generic low power state, whatever that may mean for that particular device. And then you've got off, where power has been physically removed from the device. Now, even after you turn on the power management subsystem, devices still default to active. So just by turning on power management, you don't get any savings by default. So you need to take explicit action to get improvements from device runtime. And this doesn't only apply to external peripherals as well. It's also internal SoC blocks which may be powered or enabled or disabled or whatever. So UART, SPI, whatever. Some of these are more relevant than others. An I2C bus left on doesn't really matter. UART left on matters a lot. So some software guidelines, my opinions contained inside, beware. So basically the first opinion is that basically all drivers for all devices on the board should be enabled unless you have a very good reason. And the reason for that is because, as you saw in the table, there's a difference between what the boot power is and low power mode is. If you don't have a driver for that device, there's no way to go from one to the other. And there's an argument that could be made there about maybe there's some alternate minimal driver which only contains the transition logic, which could be like a future improvement for the power management stuff, but that's neither here nor there at the moment. All instances of those devices, at least those that have a difference between the boot and the minimal power consumption, should have device runtime PM enabled. If you don't have it enabled, they will be in active mode and you will get boot, not minimum. That also implies that all drivers in that application need to be implementing PM. If you turn on PM on a device but it's not implemented in software, well, it's not going to do anything, right? And this is true for all applications, even if you're only using a subset of the hardware. If your board is only measuring temperature once a minute, but you've got a GPS modem there, you still need the GPS modem to be enabled and in running runtime PM for it to actually be put into a low power state. So luckily, enabling all drivers is easier now than it was in the past. They're basically, most drivers these days are sort of just automatically enabled if they exist in device tree and if they're enabled. Sensors is okay because most of the time you turn on sensor anyway. But for some other drivers, it's worthwhile being aware of the high-level dependencies. So what's a good example? I think like the audio codec, at least in my tree, sits under like a high-level audio option. So if you don't turn on the audio subsystem, then your audio codec won't be enabled. So if you're trying to figure out why a device isn't running or whatever, obviously check like your autoconf file. And if it's not enabled, well, start looking for some high-level dependencies or run GUI config or whatever. So how do we actually turn on device runtime PM for all devices? Obviously, you can do it manually at runtime in your application with the function PM device runtime enable. The problem or challenge with that is that your application then needs to know every piece of hardware which is going to be on your board, which is fine for a single piece of hardware. But if you're trying to run the same application across 3 different boards, well, unless you just throw a whole mess of if-defs in your like main initialization code, you're not going to actually hit all of these things. So a couple of months ago, a year ago, whatever it was, I contributed PM device runtime auto. So this is a device tree level flag. You can set it in your board files for each device where this matters. And essentially what happens then is that after your device init function runs, it will automatically turn on device runtime PM for that device and transition it to its lowest power state. So without having to do anything in your application land, your devices will automatically transition to whatever the lowest power mode they will support from the software you've written. It is using device tree to configure software in some ways that may annoy purists, but like device tree is the mechanism we have to do per instance configuration. Kconfig is not really, and Kconfig has tried to transition away from that as much as possible because it used to be like UART 0, UART 1, UART 2, enable, and it was just a giant mess. And this only does anything as well if PM device runtime is enabled. If you have those flags in your board device tree and one application doesn't need it, it will just be ignored. So there's no cost to putting this flag on devices which support device runtime. Okay, cool. Okay, so for all of this to make any difference at all drivers need to actually implement power management. As Flavio said in the very first presentation of the conference, conceptually it's pretty easy to implement. There's only a single callback that you need to actually write, and that's basically a switch statement of this is the action that some high level wants you to take. Do that thing. What do we got here? Right, so when you start thinking about power management and initializing devices, there's other considerations to take, right? Like the init function runs at boot, but all of a sudden you've got devices sitting on power domains which aren't necessarily powered, right? So what does initialization mean if you physically can't talk to the device? And how do you set up your init function to actually do that properly? Now, that's sort of a hard problem, but then when you realize that initializing the device is essentially just treating it as if you've just powered it up, well, that's just what the PM control callback is doing, right? So another thing I've contributed somewhat recently is this thing called PM device driver init. So the idea behind this function is that your core initialization code only sets up software data structures, so sets up a GPIO callback, like the structure, not the actual GPIO. It sets up like a work queue item or whatever needs to be done for your particular driver for software. And then what happens is you essentially at the end of your init function, you finish it with PM device driver init, your device, and the power management callback. And what that does is that function automatically looks at the power state of the device. Is it powered, is it not? And runs the appropriate runs the appropriate actions to bring up that device properly. So if it's powered, it will run PM device turn on. If it's not powered, it will just do nothing because there's nothing to do. But the real advantage of this is that if power management isn't turned on at all, it will just run action turn on, action active, action resume. Yeah, resume. And what that actually means is that even for people who don't care about power management at all in their applications, they're actually still testing the logic of those power management callbacks. So it gets a lot more, because like, at least from my view of how people are using it, it's a relatively probably underused subsystem in Zephyr, and actually exercising these callbacks and stuff is not necessarily well tested. But in this case, it's a single flow of logic, no matter whether power management is enabled or not. And that really simplifies drivers and actually supporting it properly. Oh, sorry. The other thing to do in init is to configure the hardware as if it doesn't have if it doesn't have power applied, whatever that may mean in that context. Probably it means driving GPIOs to like ground instead of floating or whatever. All right, so you've got your hardware, you've got your software, well, you've got your hardware, you've got some drivers, you measure your power consumption and you're like, oh, this is more than I wanted. What are some cheap wins I can do without, well, what some cheap wins I can get without actually doing necessarily too much work because I've got to ship next week or whatever. So UART is typically, is commonly used for like logging and shell commands. Normally that means that receiving is turned on for shell, so you can arbitrarily type on your laptop to reboot or whatever. But UART receiving is a power hog. On the 52840 at least, receiving, like having the UART receive running is just 1.1 milliamps immediately. So that's like, what, 200 times more than what our baseline current consumption is just for turning on the UART shell. If you don't use the UART shell, there's no reason to have that running, right? So you can turn it off. A lot of these things are Nordic specific because that's what we typically use because they have sort of great idle behaviors. For Nordic, many peripherals depend on the high frequency clock when they're enabled. So if you leave, say like the SPI bus on, I may get this wrong, if someone from Nordic can yell at me if I do. But like if the SPI peripheral is still on, even if you're not using it, the high frequency clock is still on, and that costs you some amount of current depending on the crystal you've got connected. So turning off things, even if you're not using them, turning them off can get you wins. This only helps if you're turning off everything which needs the high frequency clock. If there's still one thing that needs it, you're out of luck. This is back at the hardware design stage, but internal oscillators, generally a bad time for everyone. Poor accuracy, poor stability, and they draw a lot of power. DC-DC converters, if you've got them on the board and you've populated the inductor and the capacitor or whatever, make sure you're like turning on the K-config options or whatever that actually enables it. Converting the energy instead of burning it in an LDO always helps. LEDs are, they're nice and pretty and make users happy, but they also draw a lot of power, especially for something like a coin cell where peak current is limited. Bright LEDs can easily hit 20 milliamps, and if you're using like one of those NeoPixels and stuff, your power measurements go out the window. So toning that back as much as possible is definitely a win from a power perspective. So iterative improvements. So okay, you've looked through the cheap wins, you've saved some milliamps or microamps or whatever, but you're most likely still not hitting the theoretical minimum of your hardware. So what do you start doing next? So this is where this table where you create back at the very start of the process really comes in handy. Because basically what you can do is you can run your sample application and go, all right, sweet, it's using 30 milliamps currently. You look back at your table and go, okay, well, what's a peripheral where like there's a 30 milliamp difference, right? And you go, all right, sweet, it's using 30 milliamps more than I expect. My GPS uses 30 milliamps. That's probably the cause of the problem, right? Not always the cause, but a lot of the time it is. So essentially, yeah, calculate the difference. iterate over those potential causes, like turn on power management, turn off power management, see if things change, try and just narrow down the problem. Obviously, the individual problems are many and varied, so I can't really provide general software development tips, but yeah, basically, like you try and resolve the issues one by one, as you do with any problem. And then you keep repeating until the measured current matches what you expect. Now, because this is actually because you're looking at the total difference, this actually gives you the biggest wins first. So if you're time limited, this is actually quite a useful way of doing it. Because if you've got something which is using 100 microamps more than it should, you're not going to notice something that's using 10 microamps more than it should, right? You're going to end up fixing the 100 microamps first. And this process also ensures that there's no sort of regressions as you fix one driver, right? Like you fix one driver and the power consumption goes up, you're like, oh, something else is going wrong. This is actually basically what I just said. The one thing to keep in mind is that if it's using 100 microamps more, that could be 2 drivers using 50 microamps more, right? So it's not always a one-to-one mapping, but it's a useful first thing to look at. And if the driver doesn't implement PM, implement it. If it already implements it, yeah, get and put the device while you're measuring the current. If you get and put the device and the current consumption doesn't change, well, you know something's going wrong, right? Pin configuration. So floating pins are a pretty common cause of like just weird current consumptions. So down the right there, you can see like that's a power consumption, like a current curve, not a voltage curve. And it looks like weirdly analog, and it's, it doesn't really match what you would expect. And this is typical of like the back powering problem that I mentioned back at the start. Like just floating pins in general, weird analog voltages, digital devices don't like that, and they have odd behaviors. So if you see something like this, it's probably a pin configuration issue. It's not being driven low, it's not being driven high, something like that. Another typical cause is just like there's a voltage across some resistor somewhere, right? So if you, if you see that, okay, my power consumption is 100 microamps and my system voltage is 3.3 volts, well, do I have any 33K resistors? Please don't correct my maths. Like, do I have any resistors of that size on my board? If you do, go around with a multimeter and just see if there's voltages across that, because you may find that, yeah, like some pin you didn't realize you're driving low when the other side of it is high, and that's, again, a sort of easy win, right? If you are using power domains, make sure the power domains you expect to be off are actually off. If they are still on, it's potentially because of unbalanced get and put. So if you request the device twice and only release it once, well, it's going to stay on. And if you start running out of ideas, grab a multimeter, start poking around and see if you can find any weird voltages, because that often leads you to other root problems. So if you find 1.4 volts on a 3.3 volt board, you probably need to look into that. If you find 2.5 volts on a Nordic LTE modem, that's the reset line. Don't worry about it. When you start getting super frustrated, you start looking at errata documents. This should probably be a thing you look at earlier in the process, but I always end up forgetting. And just do a brief skim for anything which contains the words power or increased or whatever. And then at that point, you're like, okay, well, does it apply to what I'm actually doing? And is there a workaround already being applied? So I've picked on Nordic here because they have nice documentation and it was the easiest one I could find. But in this case, if you just try and stop a timer, it's high power consumption. If you're using timers, that's bad. If you're not, doesn't matter. But yeah, errata is most of the time it's not errata, but when it is, it's really annoying. Other things. Maybe your board is perfectly fine. Is there an LED on your programming adapter? For that Loki board, when you plug it into the programmer, it's an extra 300 microamps because there's a little blue LED on there which tells you it's powered. So like, you've got to keep that sort of stuff in mind, right? If your JTAG is still physically connected to the device, that's going to add 30 microamps because they've got an internal resistor on that VDD sense pin, right? So if you're sitting at 30 microamps above where you are and you're tearing your hair out, but your JTAG is still connected, well, there's your problem. And it was nothing to do with your board or your software, it's just the measurement setup, right? If you're running GDB or RTT, that's easily going to add milliamps. Again, picking on Nordic for the LTE chipset, if you connect GDB and then disconnect, it doesn't go back to low power. You need to power cycle the thing. And maybe your test board is just physically broken. Try another one. Hopefully you got more than one. And the other thing is that like, when you start getting down to the really low power consumptions, the environmental temperature actually does matter, or at least I'm pretty sure it does. If you measure one day and it's 4, and one day it's 4.5, and the next day it's 3.5, probably don't worry about it too much. It's probably just something environmental, or your measurement hardware is warmer because the cat's been sleeping on it or whatever. Right, so I've been speaking lots of software things. So basically, after applying all of this stuff, again, I'm aware you probably can't read the numbers. So this is the development platform. The spikes are like just waking up every 10 seconds to go, yes, this thing is actually alive and not just powered off. So you average the power consumption over that time window, and the average there is 6.1 microamps. So I lied a little bit in the title, 6.1, not 5, but I measured it the next day and it was 4.9, so what are you gonna do? Okay, so we've got a nice baseline. Our board is now low power. Are we done? Well, no, because all you've got is a board which is low power. It doesn't actually do anything useful yet, right? So yeah, our board boots into low power state. After you start using things, will it return to that low power state? Because it's not the same thing. So the sort of flow you want to go is, okay, well, can I at least get it to low power to start with? And then it's, okay, after I use the parts on the board, does it go back to that low power state? And only at that point you're like, okay, right, my board is good, my drivers are good. Now I can start being smart about the application and turning things on and off when I actually need them. So a really good tool for doing this is a validation application. And basically the purpose of this thing is it just uses every driver on the board, right? It writes to flash, it reads from flash, it turns on the accelerometer, it reads samples, it measures the environmental temperature, it tries to get a GPS fix, whatever. Whatever's on your board, it should be using in whatever way it possibly can. And then you let that application run, and then when it's done, you measure the power consumption again. Is it the same after as it was before? If yes, absolutely great, because it means your drivers are good. If not, it means that, well, your transition up from low power might be good, but maybe your transition back down to low power has missed the GPIO or has left the SPI bus on or something, right? And because we know that the board is low power when it boots, it actually makes it really easy to find out where that problem is, because you just turn off the test for individual drivers, and as soon as the board goes back to low power, you know, that's the driver which is causing my problems, and that's when you go dig in. And this is not only for like testing low power, right? Like you have an application which validates that the board boots into low power and that all of your stuff on the board works. That sounds like a great idea for like a manufacturing test application, right? Well, this is basically what I just said. Yeah, disable test until you find a misbehaving one. Yeah, great. All right. Your hardware's been proven to be low power. Your drivers have been proven to be low power. Now it's time to write application firmware. And this basically comes down to think critically about when data is needed, request things when you need them. If you no longer need them, release them. If you're getting a GPS fix every minute, but you only ever want to send it every 5 minutes, well, why are you doing that, right? Like, it costs you energy. And that's just like, that comes back to application requirements and just being smart about what you're doing. But basically, as you keep developing, keep profiling that application and compare it to the baselines. Normally, in your application process, you can find a spot in time where it's not really doing anything. And you can sort of measure that power consumption and go, okay, well, when my application isn't doing anything and it's still either the minimum power consumption, or I understand why it's not the same thing. All right, that's it. Any questions? Hopefully that was useful.
Hey, thank you for your talk. It was very interesting. One question about the device tree option you mentioned you introduced. It's not used when the kconfig option is not enabled. What would be the potential cost of having that as a default for everything?
The cost, I suspect, would be, I think a power management subsystem just prints out warnings when you try and turn it on for something which doesn't have it enabled. The actual cost, I don't believe is anything. That's a good point. I hadn't thought of that. There are some drivers where the power management stuff is sort of abused in some ways to do things non-standard. And I'm as guilty of that as anyone with out-of-tree stuff. So you may cause problems there. But in general, it's probably a good idea. Well, it would be a good idea if power management was sort of more supported, I guess, in drivers.
So if I wanted to study a particular driver that does a really good job of power management, do you have any recommendations? Like, is the BMA 400 a good one? Or is there even maybe a whole open source application that does a good job at low power as a reference?
Not that I'm aware of. So I'm not exactly proud of this, but a lot of those drivers there, even though there are drivers in tree, I'm not using those drivers in tree because power management, a lot of this stuff was written several years ago when power management was in a worse state. And I have my own APIs for accelerometers and stuff, so it doesn't really make sense. Like, there's actually relatively few drivers in tree that do this properly. The SPI flash driver, SPI NOR, does a decent job if you ignore the idle and deep powered downstate stuff. But yeah, the SPI NOR is the one that comes to mind because it does the PM device driver init, and well, it doesn't turn on the device tree flag, but yeah, it does the software properly.
So it's regarding the first question, why this option it's not enabled by default. So the reason it's because there are two types of power management for the device. There is this, that it's the runtime power management, but there are certain devices that don't use this, that they use the system managed power management for the device, that it's basically, they want it to be suspended only when the SoC it's being idle. So if you enable this, definitely this will mix it with this other behavior. So the device has to, opt to select this option if it's really needed.
Yeah, thanks, Flavio. Yeah, sorry. The Nordic SoCs don't actually implement system power management, so I sometimes forget about it when I'm talking. But this is device runtime power management, not system power management. And yes, that option would conflict with. Yeah.
So thank you. It was a great talk. So once your application is doing everything that you want and so on, and you reach the expected level, how can you ensure that there are no regression in an automated fashion on your following developments? Do you have, without having too much complex hardware stuff to?
So I missed part of the PyTest talk that was yesterday, and we don't currently have like hardware in the loop testing for this sort of stuff. But it was definitely on the roadmap to sort of get hardware in the loop testing in CI, where essentially the only application that really matters, well, not the only one that matters, but the one for the most bang for the buck is that validation application. If your CI runs that validation application, it tests all your drivers, and then you have a Nordic power profiler kit on the end of it, or an Audi Arc, or whatever you've got to measure power. you could hook that into PyTest, and after that test is finished, measure the power consumption, and then validate that, push it to the cloud somewhere, whatever. So you could track that over time. Applications are more complex because depending on the point in time that you measure it, you're going to get different values unless you average it over like a representative time thing, but that may take too long for CI. Like, basically for us, we make a new release, flash it, and then hook it up to our power thing for a few hours and just go, is this still what we expect?
Okay, thank you.
Thank you for the presentation. I've got a question in this iterative process in which you're trying out different drivers and devices. Are there any means on Shell right now to get the state of the device, the power management state, and probably like try to set it to these different states to actually see interactively as you're optimizing towards that? I'm wondering if that's something that's in the tree right now.
So there possibly is, but this comes back to sort of in the cheap wins part, right? Like UART receiving is expensive, and so that may be helpful for stuff like a GPS driver, but when you're trying to get down to the lower levels where the difference is like 10, 20, 30 microamps, those differences are going to be swamped by whatever the UART is doing, right? So the shell sort of implies that you have UART turned on, right? And most of the time your problems are not with, oh, I forgot to turn my GPS driver off, because that's blindingly obvious. It's with the last 10, 15, 30 microamps, and you can't afford to have the shell on when you're doing that.
Cool. Is there anything that you can do with simulators to help reduce power usage? Like, is there any sort of testing that you can do on a simulator before you get access to the hardware?
I mean, anything is possible. It's, like, just conceptually, I think it's a hard problem because, like, hardware is complicated, and trying to simulate, like, or trying to emulate, I guess, the behavior of different devices, like the amount of time it would take you to write a simulator for, like, a U-Box GPS modem, like, that's going to be like a multi-year effort, right? Because, like, that's what their company is. It's a simulator which they turn into an actual thing, right? There's possibly some easy wins, but for us, especially with, like, when we've done multiple hardware, like, platforms, there's a lot of commonalities between the platforms in terms of peripherals. So you actually most of the time have most of the drivers you already need. So there's not, waiting the extra couple of weeks for the hardware to arrive is not normally a huge deal, because you have a previous hardware iteration, which is mostly what you need. And if it's not, you buy a dev kit, whack it on the shield, and, you know, it's not ideal, but it's a hard problem to solve, in my opinion.
Okay, two final questions, I think.
Just a short comment on that. I'm working on a simulation framework called Renode, and we've been discussing that in multiple contexts. The problem is that it's very SoC specific, very hardware specific, but if you're working on a series of products or similar products, what you can do, and what we've been experimenting with, is just by analyzing which peripherals do you access, which registers do you access, try to do some kind of get comparative results between different versions of your software with some additional knowledge about the SoC, about the device configuration. You can try to reason about it. It's of course not ideal, but you can get comparative results between versions of your software, and that gives reasonable results.
So now that you've gone through all of this process multiple times, contributed quite a few features to the power management subsystem in Zephyr, do you think we still miss functionality there? What's the future of power management, specifically device power management?
Yeah, so back when I first started, however many years ago that was, I had a whole host of stuff out of tree for power management, especially like at the subsystem level. These days, there's barely anything, if anything. I think the core of power management, at least device runtime, I'm not really plugged into the system stuff, I think device runtime is in a really good spot. It's got the functionality it needs. It solves problems. Where the project as a whole is lacking, I would say, is just driver support. I really don't see any drivers upstream that, there's very few that actually try and do it properly. And I think it's because, well, a lot of sensors and stuff are just contributed by passers-by. They probably don't have the hardware set up to actually measure that, and even if they did, they may not care. So, like, I don't think it's worth blocking sensors because they don't support it. But, yeah, it's up to the people who care, I guess, to improve that situation.
What about the built-in the SoC IP blocks? Are those usually well implemented in terms of power management, as per your experience?
Are you trying to get me to praise Nordic? Like generally,
No,
yes.
no. I'm saying in general because you use other chips as well, don't you?
Not actually for SoCs, no.
Okay, all right, fair enough.
Historically, deep pass, yes, but that wasn't Zephyr.
Right.
Yeah, for Nordic drivers at least, yes, powering things on, powering things off works well. Pin control as well has also been a big improvement in this respect. Because some of the out-of-tree stuff I had was, okay, well, I turn off the SPI bus, but now I have to manually configure all these pins into weird states.
Right.
Pin control solves that, which is great.
Yep.
Which helps with those like floating pin issues that we were seeing. But yeah.
Great. Glad to hear that.
Okay, we are on time.
Phil wants a Dixie question, Daisy Dick, whatever the no.
This is just a sort of a comment, but one thing that I think you missed was the final nuclear option of having to desolder off some chips.
Sorry, yes.
Because that does, sometimes chips lie about their absolute minimum power.
If you no longer have any hair left from ripping it all out and you have a suspicion based on whatever, you grab out your soldering iron, you pull that chip off and see if it fixes it. You don't like doing that, and if you have one, you may not want to do that, but it's a solution.
Okay, thank you.
Thank you. It's good to see there's some interest in power management. Oh, yes. Whoop.
on.
Hello, everyone. My name is Daniel. I'm a software engineer at Intel, and we are going to talk about user space in Zephyr. This is the topic of the day. I'll give a very brief and simplified overview of user space in Zephyr, and then I'll talk about how you're going to share data using user threads, and we'll go into some brief details on syscalls, on basically how you use kernel services from user space, and then we'll go to talk about why and why not to use user space, and we'll end with some Q&A sessions. Well, for user space, the idea is kind of simple in a sense. You have kernel mode and user mode, where in kernel mode you have elevated privileges. Basically, you have access to everything, like all the hardware devices and all that. And user space have the user mode. In user mode, you have limited access. Basically, have a very limited capability to make sure that they cannot do bad things in a sense. So kernel mode sometimes also refer to supervisor or privilege mode, and user mode is kind of unprivileged mode, but usually the hardware vendors usually just call them user mode at that point. User threads, once it's user mode, kernel threads, one in kernel mode, and most of the subsystems, once in kernel mode, device driver, when you're calling the device driver API, they need to be in kernel mode most of the time because you need to access the hardware, like have a register and stuff. And of course, the core kernel has to run in kernel mode, like the scheduler or that kind of thing. So, and when I say this kind of the concept is simple, it's because really it's this. What you are limiting in user mode is basically limiting the user threads from accessing certain memory. Well, not exactly the like memory in terms of like SRAM or or like a memory map flash. It's just limiting the access to memory addresses, which means like MMIO, hardware register space. You can have a memory mapped flash area, that kind of thing. So for that, like I said, in kernel mode, kernel threads have access to all of this. That's the user space model in Zephyr. For user thread, it's like you basically grant user threads access to certain memories, certain memory regions. For example, the left two can access the memory region of the left two, and the right two can access the right two. And when the left two user threads try to access the right two memory region, the hardware blocks the access to it. So at least for the current model, if you try to access it, it will create a page fault mostly, and then the user thread will be terminated. And because of the user that doesn't have access to everything, and by default, it has no access to most of the memory. It has basically only have access to like the text region, because you have to execute code, and the read-only data region, and also its own thread stack. So how do you share data between user threads? So for example, we have something like this. You have, say, 3 groups of threads and 4 groups of data. They are logically partitioned. For example, you have a bunch of data that's like coming from a sensor, from one sensor, and another set of data coming from another sensor. And then you have a group of threads processing the data from both set of data. The process of sharing is mostly at build time. You can do it at runtime too, but well, the first step is that you assign data to memory partitions. So a basic group, like for example, the memory partition A has that 4 pieces of data, memory partition B, C, and D, and so forth. And then you create memory partition with reference to those memory domains. You create memory domains with reference to those memory partitions. But at this point, the memory domains are not complete. And you actually have to assign threads to the memory domain for them to be complete, because memory domain with no threads, it's like there's no purpose, because the threads are running within like the concept of memory domain, so that everything in that domain can be shared. And this is kind of the relationship between memory domain and memory partitions. Basically, so here you can see that for memory partition A, the threads from memory domain 1 and 2 can read and write the data in memory partition A, and then for memory partition B, only memory domain 2 can access those, and so forth for C and D. You can see the arrows, like, because here it's like when we create the domain, the memory domain, we assign the memory partition to those domains. So in a sense, here, so we have this. And it's kind of like a very simplified way of describing memory domain and partition. The actual setting them up requires a lot of like linker magic in a sense. So please refer to the online documentation for the examples on how to actually do this in the code. And one thing to remember, global variables cannot be accessed by any of the user threads. They have to be in a memory domain. So if you just declare in the C file, no user threads can access it. This is how you share data between user threads. The next topic is syscalls. The main purpose of syscall is for user thread to access kernel services. For example, you want to log a mutex, unlock mutex, give a semaphore, send something to the mailbox, that kind of things, and also like when you want to access devices, like you want to do I2C transaction or send something to the UART. And in the Zephyr model, we call them kernel objects. Here are some common kernel objects that's in Zephyr, like, for example, mailbox, memory slab, mutexes, the kind of things. But for device driver, remember that each kernel object is not the device driver themselves, but each device driver instance. So, for example, if you have, say, 3 I2C controllers on the hardware and they are enabled, you have 3 instances of the I2C controller, and you have 3 I2C kernel objects. And similar to memory access, like similar to what the memory access model, user thread has very limited. You can restrict access from user thread to each object. Actually, in a sense, in actual usage, you actually grant access to each kernel object to each user thread. So the model is for kernel thread, they have access to all kernel objects. But for user threads, you have to explicitly grant access of a kernel object to that thread. So so for example, you have 2 mutex, you define 2 mutex, and then you assign them to 2 threads, like individually to 2 threads, and each thread cannot access the other mutexes. So that's basically the model for the kernel objects, and the syscall is, in a sense, in practice, runtime is not cheap. For example, it's like they just highlighted. This is basically the flow chart of the syscall, how syscall is being done. If you're already in kernel mode, like you're in kernel thread, it's easy. You just go straight to the implementation. Just one indirect call to the implementation. In addition to in addition to running it in the kernel thread, this path is also taken when you are in interrupt. So while you are in ISR, this is also the path that's being taken when you do a syscall. So for example, don't do mutexes, don't log or unlock mutexes in ISR, because you may deadlock the system. And then for the user mode, this is actually a kind of a simplified flowchart. I leave out a lot of the core function, but the basic idea is that you have to go into kernel mode to basically execute the implementation. So the first step, like if you're in user mode, the first step is to package the function argument. And then it goes through the previous escalation to go from user mode to kernel mode. So you can use a different set of permission, like a different set of page table for MMU and different set of memory region permission for MPU, for example. And then after previous escalation, you're in kernel mode, and then you have to unpackage all the agreement, all the function arguments into basically just the elements. So for if you pass 64-bit data with on a 32-bit system, you have to the background has to unravel this. It's like pack it in a certain way and then unpack the data. So after unpacking the data, it has to go through a verification to make sure that the data being passed are valid. For example, if you try to pass a mutex, this verification has to verify that this is a mutex. You cannot just pass in any arbitrary memory address and call it a mutex. No, that's not a good thing, because you would be modifying arbitrary memory in kernel mode, which basically has to have access to everything. So this verification must be done. And another part of this, like if you are passing something, you're passing a memory buffer or a string, for example, in this stage, you need to copy. You need to copy that, basically allocate memory in kernel mode and copy the memory buffer of the string into the newly allocated buffer. This is mostly to prevent something modifying the buffer between the syscall and the actual implementation is being done. It's kind of a security measure too, because with a preemptive threat, the threat going through this can be preempted, and then some things can come in and modify the buffer, and then the original thread comes back in, run with the modified data. You don't want to do that, because the data can be modified in a malicious way. For example, like Bluetooth, you can massage the package in a sense to do something bad. And I don't have the return path for this, but the return path is very similar to the path here. It's just in reverse. So you package the return value, go through the previous de-escalation process to go back to user mode, and then unpackage the argument in a way so that the site of calling this function acts like it's just another function call. So this call is kind of hidden, like behind the scene things for the caller. After seeing this flowchart, someone might ask why do we need user space? There's always the big question is, why do I care? One very first things on why or why not using user space, or basically why not using user space, the hardware must support MMU or MPU, memory management unit, or memory protection unit, or in the RISC-V world, it's called physical memory protection, if I remember correctly. If you have no MMU or MPU, you cannot use user space, because you don't have hardware to guard the access to the memory. And another thing, like with the syscall flowchart, you can see like the latency goes way up for user thread. Like not just only syscall, but for context switching too. Even if you're switching between user threads, you have to change the page table, or you need to reprogram your MPU for the permission of the incoming thread. And another downside of using user space is that the memory usage requirements goes up, because if you're using MMU, you need to store the page table somewhere, so you can swap in and out doing context switching. And then for user thread, there's an additional stack that is needed for user thread, because when you're going into kernel mode, the execution is no longer using the user thread stack. It uses the previous stack to, in a sense, to avoid leaking data through the stack. And at least the current implementation of all the MMU code is that the previous stack is set up in a way so the users cannot access to them. They, kind of like kernel thread. It's kind of like kernel thread. Only things the kernel mode can access the privileged stack. And also, one thing to consider is the page alignment for memory partition, because the access granularity is on the for MU is on the page size. It's like mostly is 4K, but for MPU, it might be it's based on the MPU. For example, if you have a power of 2 requirement, so you always have to pad the memory partition region to the power of 2. So if you have, say for example, 4-byte data and the alignment need to be 8K, then you're almost wasting 8K of memory for that. And in addition to this, when considering whether to use user space, you have to understand the thread model that the user space implementation is based on. Very first thing is that there's no interactive user. I don't know why you want to have interactive user on an embedded system, but that's the model. No interactive user, no login, and another thing is that the threat model is that we are not guarding against malicious code. Although the threat model says that we don't trust the code running in user mode, however, because you have to package the whole firmware together, so if you don't trust the code, why are you packaging it in the flash? So that's the original model. That's the original model. However, with the linkable module now, things get a lot complicated because you can basically load whatever code in there. So that's the next talk. Kind of plugging in here, but that's the next talk. And another thing about how the threat model is that it's, like I said, not guarding against malicious code. Most of the time it's just kind of just preventing coding error. For example, instead, well, I think kind of like some of the common error in terms of memory access that you do some pointer math, you add a pointer and a size, and if it wraps around, then this is something that you want to catch and fix it in your code. So instead of it trying to access invalid memory. And the other thing is that it just isolates between memory domains, so that basically, so the bad behavior, in a sense, of the threads in one domain will not affect the behavior of the threads in another domain, as long as they don't share the same memory partition. Because if they modify the same data, and then one group is writing bad data, and then the other group reading bad data, then there's not much you can do there. So I think that's a very brief and simple overview. I hope you're all confused.
So not a technical question, but rather since in our own applications we don't use user space, I'm just curious if you could name a couple of real-world practical applications where this is being used.
Real-world, something I cannot talk about it here. But I don't know any commercial product that's using it, but that's mostly because of my ignorance. And one thing I just want to mention is that what we are providing is just a framework. So whether you want to use it is up to you based on your requirements, like what your product is doing. So I actually follow an example to this. Like if you have a sensor package that you put it into a remote location that you just go there and grab the data once a month or once a year, and they don't do any like data transmission or receiving anything, you may not need user space because you don't, because you're not getting, you probably will not get malicious data that compromise the operation of the whole thing. So I think it's
so
yeah.
Just to answer this question, I think what Daniel mentioned with regard to loadable extensions, which is something new in Zephyr right now, but it is definitely something that has been done outside of Zephyr in the context of Zephyr. Right now we have something, but it's mostly, I mean, when you want to use an MPU or an MMU, it's about guarding like a basic firmware from third-party data that you might actually you have in the system, through, extensions, codecs, whatever. You want to allow firmware extensibility, and that's like one guard. But also the practical solution, and that actually basically was going to be my question, is all of the things that were listed on the slide. It's actually, there is a lot of things that we, in Zephyr, that we have right now where, because of historical reasons and whatnot, I mean, we don't have much of error checking, for example, yeah, or parameter verification, etc. I mean, that has changed over the years, but things that we couldn't put in the implementation that is used in the non-user space case are available in the verify function. If you go to the syscall diagram, you see there's verify. Yeah, depending on the function, there is a lot of error checking happening there. Yeah, and if you are running a safety critical application, or that's actually something you want. Right now, however, and this is my question actually, yeah. Right now, however, this is all depending on user space, yeah. We really need to figure out a way how to start moving a lot of verification and checks that we have in this function that is enabled right now in user space into the main implementation. We did that in the past with the check if macro and stuff like that to avoid explosion in the footprint usage. But we need to figure out a way, yeah, maybe we should have like a two-level thing where the implementation and you can actually enable the verification function if needed to add more checks, yeah? So this is a question, and I briefly talked with Daniel about that. This is not so easy because with the design. My second question is, what are the differences in the implementation when you have an MPU versus MMU, yeah?
The difference between MMU and MPU? Well, at least most of the things are common between MPU and MMU. So threat isolation, memory domain, we all have that. I can't think of any major thing except that with MPU you're limited with you're limited by the number of regions in the hardware. So you have to be very careful on how you structure your memory to minimize the number of regions. But otherwise, there's always, not always, that's one issue about whether threads in the memory stack should be able to access the thread stack of the other thread in the same domain. If I remember correctly, the introduction of that actually got introduced into when we introduced memory domain, so that every thread in memory domain can access the stack of other thread stack in the same domain. But the thing is, the ARM MPU implementation is I think it got implemented before all the memory domain things, so it has third stack isolation already built in there. So there's some difference between the actual implementation, but otherwise, at least in facing the user-facing part, the developer-facing part, if you're writing an application, they should mostly act the same.
I was going to interject again, just riffing on us. Going back to the syscall chart, which was all like great, and it shows all the things that need to happen. I think the marketing side of this, though, that I think got missed is that this is all invisible to app code. I mean, one of the things I think we have done best on this, and this is all Andrew, our dearly departed Andrew Bowie's work. I mean, he didn't die; he's at Apple. You know, for the most part, if you've got an app and you need to get, you know, some kind of transaction into kernel code to pass an argument or whatever, you need to add a new syscall. You just declare it as a syscall, you write your validation function, and you're mostly done. And then if you've got data that you need to pass that's not arbitrary, then you might have other stuff to do. There's a function you need to call to copy the data out. If you need to add another kernel object, that's actually kind of a mess because you need to go and edit a Python script right now. But really, I mean, all of the functions, the entirety of the Zephyr API for the most part is exactly the same in user space. Now, again, performance-wise, that can be very different. But really, I mean, I think we've got a much stronger story here than I think really any other, you know, embedded OS, and frankly, even than like Linux does. You need to get into kernel space in Linux. It's hard, and you've got lots of tools, right? You can choose, like, you know, a sysfs node. You can put something in proc. You can do all kinds of things. But you're looking at, okay, here's your 6 function calls that you've got to implement and all the callbacks and all of that stuff. And in Zephyr, it's you go and you add one preprocessor token and you're done. So
actually, extending to that is like even if you declare a function in syscall, like line this says, it's like it's all behind the scene. So even if you set config user space to no, at least from the API user perspective, they don't need to change anything. They can still call kmutex log. It will function the same in their perspective.
Thank you for this presentation. I just have a question. So if you access something in another memory domain and you don't have the permission, you mentioned that the thread will be terminated. This is the case on both MMU and MPU.
Yes, because it will, well, at least on the MMU term, it will cause a page fault, which goes through I think it goes through C fatal error, and then you eventually call kthread abort. On the on the MPU side, the hardware may call it a different, like permission, like privilege access denied, that kind of thing. But the mechanism is still the same. The idea is still the same. It goes through C fatal error, and eventually it will call kthread abort.
And the scheduler will just select another thread. It could be in another domain.
Yeah. When it returns from the fault, it will. You will select if you're using the switch, you will try another switch. If you're not using the switch, I'm not familiar with that part of the code, but yeah.
And I suppose if it was essential, it will just terminate it will just do a fatal error. It was marked as essential thread. Okay, thank you. Just also another question: would you consider a good practice to put the whole code in a module and use library app named instead of just creating the different partitions? Just put the whole memory domain in a library instead of just creating each memory domain manually with the different partitions.
There's an API that the app has called, basically gives you some preprocessor stuff where you just declare, you know, this variable goes in this domain.
Okay.
So maybe it's strong. Yeah.
Thank you.
Do we have any tooling or anything that helps, you know, visualize to some degree simply like just the memory partitioning layout for, you know, for someone who's trying to set this up? And so whether it's things like the alignment restrictions and saying, hey, maybe if you ordered these, you'd be better off and not waste as much space or anything of that nature?
No, we don't.
Okay.
At this point. Well, but we have something like this to memorize the placement in the linker strip, but that part doesn't depend on user space. We have I don't remember, it was done a couple of years ago.
As a developer of a driver for a peripheral that is really custom and doesn't use a standard API, how difficult it is to expose my code in user space? Do I need to worry about all the marshalling of the arguments, or will this be transparent, like for the other system calls?
You don't have to worry about the marsh, like the left 3 and the marshalling. You don't have to worry about it. It's done behind the scene. What you need to implement is the verification function and the implementation, and declare your API as a syscall.
I have a question. So there is a set of related technologies like this trusted firmware RAM and trusted execution environment. So if I were to explain to our customers and users when do you use the user space and when do you package your custom code in the trusted execution environment, would you have any advice, or this is just something you're not familiar with?
To be honest, I'm not very familiar with all the trust zone and that kind of thing. So I'll refrain from commenting.
User space is portable. If you need to run on a different architecture, it's what you choose.
Yeah, here's another question.
Yeah, just a quick question. You said in your slide that there is no users in Zephyr. Do you know if in the future there will be, or it's not planned at all?
Personally, I don't see this use case for having a user on an embedded system, but.
Well, I can tell you, if you sell a product, maybe you want some of your customers have some engineers, so they want to access the product and do some stuff. But then if your product is doing something bad and you want to send another people, like maintainers, they want to have access to other features. So the engineer will log in as an engineer and will do some stuff, basic stuff, is know-how. And then if you want to send a maintainer, he will log in as a maintainer and can access more features and can do more stuff. That's something that we may need.
I don't know, but like as a personally, I think you're stepping into the Linux territory. Like as a.
Yeah, I mean, but to his point, I mean, there are MCU platforms that are, considered crossovers, and as such, they're fairly powerful. And I can envision something like that, or having a display with the user input to it, and you want to kind of partition that off in a way that is not going to, someone's sitting there screwing around with it, trying to see how they can break it, right? And it's on a critical system behind it.
Well,
but I think one of the keys here is if you determine that you have a product requirement for it, then this is here. It's transparent to the application, and the only cost is the overhead of the marshalling, the escalation, all that path right there. And if that's acceptable for your application, then that's what you're going to do, because if it has that requirement.
I'm just thinking out loud here. Well, you will have to implement, like, for example, maybe as a server, you would port it over to Zephyr, something like that, or login terminal, that kind of thing. So the user space framework doesn't prevent you from having users in the system. It's just that the threat model, what is the threat model that the user space implemented is based on, does not. What was a good word for this? It's like it's just not the threat model. It doesn't. it doesn't have that use case in the threat model, and we don't really code for that at this point. So if you have something that the user space is not adequate for use case, feel free to create an issue and post it on the mailing list or Discord so we can talk about it.
I think there's an issue already, just to mention. But actually, it would be wrong to say that Zephyr does not support users, right? We have one single user. We actually have shell, and we have like recently you can do all kind of crazy stuff with the shell that almost looks like you are logged in a Linux system sometimes, yeah. But my question is, I mean, this is like just this syscall slide is actually very, as you said, it's simplified. A lot of things is happening behind the scenes. So when we build Zephyr, everything builds, etc. Obviously, we know there's a lot of complaints about the multi-stage build, but we do that not only for user space, we do it for so many other things as well. But I mean, is that a lot of overhead when you enable user space, and what actually goes behind the scenes? Is that, I mean, how complex it is to get things right to operate in this manner and using this workflow?
Well, I'm very biased in this instance, so I would say that it's not exactly easy, but it's not that hard, because the things you need to implement is the verification function to make sure that everything, the function arguments are valid before you send it to the implementation. And we have examples, a lot, not exactly a lot, but we have example in the documentation, and we actually have a lot of implementation or verification in the code itself, so they can serve as a learning material in a sense. Otherwise, as a developer, one of the things that intermediate difficulty, but for the build system is there. It may take a while. Well, in terms of building, it might take longer because it has to pass all the file, look for the syscall, and then generate all the behind the scene functions. So it's not free.
All right. Yeah, we're actually at time, but let's give a round of applause for Daniel. Thank you so much.
Thank you.
Hello, everybody. Go ahead and get started here, I think. Yeah, so this is my talk on extending Zephyr at runtime. Many of you probably know me, but if not, I'm Tom Burdick. I work at Intel Corporation. So what is LEXT? And I'm going to name it. I know it's an acronym. It is an acronym, Linkable Loadable Extensions. But when you look at the name, I want you to think about Lloyd the Llama from Wikipedia and all the double L's that come along with it. We were having a great talk yesterday about what is a Zephyr subsystem. Well, LEXT is a Zephyr subsystem, and there's many of those. But it's also an ELF loader, also another fun acronym, executable and linkable format. But maybe another kind of way to put it is it's a toolbox to build and manage and load ELFs in a particular way. What's an ELF? I mean, I think a lot of us know, but this is a kind of a fun graphic. It's a file format. We've got headers, sections, section headers. But kind of some key elements in this are, we have blocks of code, instructions, ARM instructions, extends instructions, x86 instructions, whatever target we're building for. We've got data. Some of it's, constant data, constant strings. Some of it's read-write data. Some of it's, the better saved space data, right, where it just expands at runtime and uninitialized. So kind of going back to what is LEXT, right? It's an extension manager. And so, to manage these loadable runtime extensions, we need to have something. We have a couple of nice functions to do that, load and unload. Finding symbols in our ELFs. We keep a list of these extensions in memory, and some sort of like key structure elements here that we want to kind of keep in mind as part of what we're doing and managing these things. We have a name and a use count. Interesting. But there's some other fun members in here that we're going to get to. So LEXT is also a memory manager, and memory is actually really important for these extensions, as it turns out. And it has a dedicated heap. We have read-write memory. We have executable memory. And these things all kind of need to be set up in a way where we can actually go run things that we want to run the way we want to run them. So in order to do that, we need to kind of set, all right, we have our .text section in our ELF. We have our data section. Text is, full of executable code. By default, when we load Zephyr, only our initial .text is executable. So we need to do something there, possibly. We need to kind of like copy our data, our initialized data into read-write memory, so we can actually use it. We need to expand out our better save space, description in our ELF. It's not actually in there. We just have a section size. And our read-only data. So, right, when we load all this stuff up initially in Zephyr, there's kind of two options that we can do. Today, we can either enable, if we have our MPU or MMU enabled, we need user space enabled. Or we can just not use any sort of hardware memory protection. The big part of that is, okay, well, if we would like to actually execute code in an extension and jump to a random address, basically we just load our ELF file, we copy things in, maybe somewhere in there, and I say, oh, jump to my hello world function. What's going to happen by default is there's going to be an exception because that part of memory is not executable. So we can deal with that by either, again, disabling memory protection entirely or enabling user space and doing a lot of what Daniel was talking about in his last talk. If you were here for user space, by setting up memory partitions in a memory domain. And part of that is you do get the option to set up memory permissions in terms of like read, write, and execute. So there's different ways we can execute that code in an extension. I mean, random code. Maybe we picked it up off the internet. Hopefully not. But if we don't have, if we want to run things in kernel space, any thread can call in there. Again, assuming that you've either disabled your memory protection hardware or you've enabled user space. Even if your thread is in kernel space, you still need to use user space to be able to manipulate those memory permissions and set up those memory regions or pages. Yeah, and so in user space execution, this is kind of interesting. Like let's say we want to try and sandbox our extension that we've loaded. So we do have, our MPU enabled or our MMU enabled. And in a way, we're kind of creating a process, kind of like a Unix process. We can't touch, our kernel memory at all. We can run code, but we can't actually touch any kernel data. But we can still run, all the new things that we've just loaded in, our data, our better safe space, our BSS, our RO data, our text, which is quite nice. So we've sort of, again, created a process. So what else is LLXed, or Lexed? It's also a symbolic linker. And this is kind of key to actually making everything work. The base firmware has, uses a macro called export symbol. And if you've seen the Linux version of this, it's very similar. Creates a section in your linker script with a sorted array of names and address pairs. And extensions can do the same thing in themselves with a slightly different macro today, LL extension symbol. And so why do we need all of this stuff, right? I mean, it seems like, we have to manage memory. We have to keep track of a mapping of names to names to addresses. And really this all comes down to, this is all needed just to simply get to hello world. And that is because ELFs have relocations. And these relocations allow you to place that .text anywhere in memory, in our case, right? So you can load your .text anywhere that you've allocated it. But to be able to do that, your executable code needs to know where to find things. Find variables, let's say in your .data or RO data section, find functions that haven't yet been defined in itself. So we get relocations like this when we see our sort of basic hello world extension. We have an RO data address to the string that we want to print. And we have an undefined reference to a symbol, print K. So when we actually go to load this extension, we need to look at this ELF and see these relocations and rewrite them with the actual address of these things, right? Either objects in memory or symbolic references to functions. So what are some key points about these relocations? The kinds of relocations that are going to show up are architecture dependent. As we kind of saw here, this is specific to ARM, but there's actually, relocations specific to each architecture. And it also depends on the ELF linkage. So as you're compiling, you can have flags to create relocatable objects, which typically you don't see when you're compiling your normal C program. Those all get linked together. But we actually end up using them in Lexed, or static or shared. Also depends on, sometimes your compiler flags can change, what kind of relocations show up, as Luca helped solve an early issue that we ran into, right, where there was a kind of a tricky relocation to do that I didn't really want to deal with right away to get to hello world, and this great compiler flag in long calls, so you only get absolute address trumps, which is made things quite a bit easier. And that kind of gets into the next point here, where these relocations do require, at times, it's not always simply like, hey, I have an address, my string is over here. A lot of times they are instructions, instructions for moves, instructions for loads, instructions for branch and links. And those instructions are encoded in a particular way for that particular architecture. So in order to update them with the appropriate address, you have to decode that particular architecture's opcode, change a part of it, and then re-encode it, which I think Cedric did a great job adding many of the ARM ones, which is very, very quite nice. So, and you know, some of these jump codes, some of these opcodes require PC relative addressing. So, if we kind of look at you know, some function call that might be in your extension, going from one function to another, a lot of times these are program counter dependent to keep them small. So you don't always have to store a 32-bit address right in your instruction. So you know, if you're using ARM thumb or extensa, right, you have a 16-bit opcode perhaps. You only get so many bits to store an address relative to your PC. And that, again, makes it a little trickier to do. If you can imagine for a moment, if that address to that function is too far away for that particular opcode to represent, now you need to create a jump table. And that's exactly why the imlong call, you know, kind of saved the day initially, right? I didn't want to have to go create a jump table. Yeah, so kind of continuing on with some key points about relocations here. These sections can be very interdependent. You know, text obviously needs data. Your instructions obviously need data. But data can actually need other data as well. And so each section that you have in your ELF file has an associated section typically with these relocation instructions associated with it. Symbolic linking at the moment, you know, kind of requires a like finding print K. We have a table, it's sorted, but today it is a linear search of string comparisons, which can take some time. I think as Cedric noted in his talk, you know, it took quite some time to load some of the ELFs. So this is maybe one of these cases where we could do a better job in the future. So loading an ELF at a high level, what does this actually mean? Well, we read the ELF file, we check out the headers, we look at the sections, maybe we copy some of them, maybe we reference some of them. Relocations are applied, those instructions are applied to rewrite opcodes or rewrite addresses, so everything looks pretty and it looks as if, you know, we knew where everything was to begin with, although we didn't. And finally, the extension is added to a global list, and at long last, you know, symbols in our extension, functions, objects can finally be referenced. We can use them, we can call into them, we can look at them. So how do we actually build one of these? Kind of a great, you know, a quick little sample here. You know, when I started first doing this, it was very nice to just be able to call the compiler directly and do object dumps and kind of see all of this ELF data. So I think it's still quite nice to be able to do this manually. Again, to sort of experiment and tinker, and as you're looking, at least as I was looking at these relocations and trying to understand it all better, this was a quick and easy way to do it without having to involve all of CMake. But since then, Luca has done a great job adding some CMake functions that make all of this very, very simple. Looks pretty much just like adding, you know, a library target in Zephyr. And you can give it a name, sources, output, easy. I kind of want to give one more, you know, let's take this to the next level though, and talk about this great PR by Ederson, adding an EDK. So let's say we want to go a step further with our extensions. We don't want to just build them in the same tree as our application. We want to package up sort of a little development kit based on our base firmware. We create our own API, maybe include some of Zephyr APIs, and now we want to pass along not our whole firmware, not our whole firmware source, but just a little part of it, a little, you know, a box of headers, CMake files, and so on that we can give to somebody else, and they can build extensions for themselves that we can load. So that's exactly what this PR does. It adds some great tooling to do exactly that. Yeah, so what are some use cases for today, maybe tomorrow? You know, I think many of these are kind of hopefully clear, but you know, we can use them for plugins. So if we have, you know, firmware that does audio, video, or sensing processing, we can create plugins to our pipeline of processing steps. We can also create, you know, isolated and updatable processes. So if we have, you know, a device and we want to be able to run multiple pieces of firmware on that single device, but have different sort of sandboxes that each one can play in. We can do that. We can create multi-tenant firmware based on a based image with the EDK involved. Quite nice. Potentially, we can also have sort of a base firmware with all our drivers, with all of our logging, everything sort of there, and we want to reload quickly. We could potentially, keep, let's say, 90% of the firmware, running in memory, and unload and load sort of a main loop that's nice and small. If we look at Arduino and their sketches, I imagine that's quite a useful case. And perhaps drivers. If we kind of look at how Linux kernel works with Linux kernel modules, there's possibly a use case here to load and unload drivers in cases where your hardware might vary. Maybe we can keep a lot of our code, some of our larger drivers on flash, and load them in memory as needed depending on the board configuration. So, right, what are some caveats? I mean, this is relatively new. There's no built-in signing mechanism today, so you can load any code that you build. There's no restriction on it today. That's sort of left up to you. It's a framework to build on top of. Debugging is an interesting story. I mean, you can debug at an assembly level. For Hello World, that's pretty straightforward. You're looking at a small little page of assembly. Otherwise, you do need to kind of load the symbols, and that can be a bit cumbersome. As noted, before, if you have sort of kernel objects, with this can be a little bit tricky as well, because some kernel objects, especially when you enable user space, want to live in a particular location in your memory at build time. That's used for perfect hash function. So when you pass your kernel object in through a syscall, it effectively uses the address of that and throws it into a perfect hash function to verify things. That doesn't exist if you try to statically declare, say, a mutex or a semaphore in your extension, and then go ahead and use user space with it. It's not gonna, it's gonna fail in a fun and not so fun way. Lastly, I mean, there's a couple other things, right? Dictionary logging is kind of a how do we do this today? Not a great answer. So some missing puzzle pieces there. Execute in place is not supported today. As you saw, we need to load all these things into memory to apply these relocation instructions that are associated with each section. That means we have to manipulate all of that stuff in read-write memory and RAM. And probably one of the things that I really kind of look forward to or am trying to work on probably next is at least having some stability in terms of ABI and syscall guarantees. Each time we build today, the syscall IDs change. So if you did want to use user space with this and solely user space with this, you have to be pretty careful not to change your base firmware build where it will change the syscall IDs. It would be nice if those syscall IDs remain the same. Going a step further, kind of creating an ABI would be quite nice. So you could load firmware, you could update your base firmware and keep your extensions the same without having to rebuild them necessarily. So I do kind of want to point out that this was not, solely me. This was quite a few people over time making this, and I think that's a real testament to open source. Prior to me, there was a PR for an ELF loader by a former Intel employee. Luca at Arduino added a lot of great ARMv7 and CMake tooling. One of my colleagues in the Sound Open Firmware project added extensive supports and dynamic shared ELF linking support with PLCs and global offset tables and things of that nature. Cedric and Benjamin has a great, I don't know if Benjamin's in the crowd, but if you look on LinkedIn and you search for Lext and Zephyr, you'll see an awesome demo by Benjamin Cabe with LVGL involved, where it loads and unloads various GUI modules. It's really quite something. So, and I kind of just glued it all together, to be honest. So, That's my talk. Thank you very much. If you have any questions, I'm happy to answer them.
I'm working with a. It's working. I'm working with a sound open firmware project, and we have proprietary libraries. Is there any preprocessing that you need to do on the ELF, or do you need to have it compiled with certain flags?
So yeah, kind of going back to the relocations, right, that are there. Not all relocations are supported for all architectures. Basically, ARM is the only one today that I believe supports all relocations, and that's again thanks to Cedric from Schneider. I believe Giannotti from SOF has added many of the Extensa relocations, because hi Daniel, I'm assuming you're talking about Extensa in this case, correct? Yeah, so I mean, I assume that many of the Extensa relocations are possible and already implemented, but if not, then that's something that would need to be done to support that. But really, that's kind of the biggest barrier, is supporting those relocations.
Hi, fantastic talk, thank you. Question about the architecture support. I guess that right now it's Cortex-M plus Extensa, or anything else?
Yeah, that's right, yeah. So there is like an architecture hook today. I think it's probably, it will probably need to be refined somewhat as time goes on, depending on like what kind of parameters need to go in there. But yeah, today it's Cortex-M and Extensa.
All right. And for the build process, because you mentioned that there is a PR with the let's say SDK, what? EDK, sorry. So do you build your extensions against your application so that all the memory limitations are taken into account, or do you build it separately? What's the process?
Yeah, so it depends on the route you want to go. So if you can use the built-in like CMake functionality, right? If you have your base for, you have your Zephyr application, you could use that to build extensions right in line, right next to your application. If you want to build outside of your main applications, that's exactly what Ederson's development kit, or extension development kit is there for, to do exactly that. You can effectively, there's a new target added to the CMake target list, right? In your base application, you build the Lex EDK. It generates, I believe, a directory, right? Or maybe a tarball. One of those. Yeah, effectively some sort of like directory or tarball that you can basically package up and give out, and that's all you would need then at that point to go and build. Besides the compiler tool chain and such, right? But that's all you would need to go and build an extension at that point. It includes all the headers, CMake, compiler flags, and so on. Yeah.
So yeah, what are the thoughts on like ecosystem directions for like complicated dependencies? I'm thinking about things that want to link to like libc++ and libraries going on and on and on, often with transitive dependencies. Like obviously, one could force apps to sit there and make a static library out of everything they're going to depend on. Is there hope to handle some of this in a kind of like the HAL directory that we have right now? Something where there's like a repository of like pre-done integrations.
Yeah, I mean possibly. Like there's no real limit on it today in terms of. So I don't know if I said this, but extensions, I believe today can depend on other extensions. If it's not today, that is a planned feature by others and myself. So you could have, like kind of the equivalent of a shared library. So if you kind of have that going on, right? Like I think Cedric, you were talking about CanOpen, which is quite large, or maybe you have a library of plugins for your particular firmware. Maybe it's audio, maybe it's sensing, maybe it's imaging, right? Image processing. I think that would be great. I think that's sort of outside of the scope of Zephyr mostly, right? I mean, that's sort of application dependent and how your embedded application wants to work. But I mean, certainly that's possible.
In terms of relocations, I know it's not a complete solution, but could position independent executables help the situation?
They probably could. Yeah, I haven't looked too deeply into those. So, you know, I understand that, yes, they can. There's sort of a cost, you know, out of that, as I understand it, though, because you have to, you know, pay like a register cost to keep around like what position you're in. You have to sort of load things in a particular place. Then, as I understand it, I'm not, you know, I haven't looked too deeply into this, so tell me if I'm wrong, but. Yeah, so I believe there's some cost to that. And that's sort of true, you know, I don't know if I said this as well, but that's sort of true depending on how you do ELF linkage as well. So if you do relocatable ELFs, you sort of get like the best possible outcome potentially in terms of instruction, like size and speed, because you're not doing additional loads and stores for like, hey, I need the address to print K. Well, I mean, as you saw, there was a separate, you know, address right in the text section. It had to go load that, then call to it. If you were to do the, you know, if you were to just build this normally, it'd be a single instruction, a BL, here's the address, PC relative, go jump there, right?
Second question is around execute in place support. Does it sound reasonable to do the relocation at the time you're saving the extension to the flash?
Yeah, I mean, I think it's quite possible. You could, you know, if you knew, I think like anything is possible, of course, right? But the way it is today, it's all very much dynamic. But you could possibly have like fixed slots, so you do like relocation for everything ahead of time, knowing that you're going to load that particular extension in a particular place in memory. But that's sort of the you know, the problem, right? You have to know where everything's going to be ahead of time to do those relocations in Flash. Potentially, you know, I had thought about, you know, maybe you could basically go, you know, this is costly, right? But maybe you could do it where you read in your ELF, knowing where you're going to put it, rewrite it in Flash, saving it back, only loading the you know, the read-write portions, and then execute from Flash still, potentially saving like the text section, right, and the read-only data section. You still have to pay the cost of the data though. So, I mean, there's some options. Yeah.
In Zephyr, I understand the build is application-driven, which means I take my application and build a single binary with everything.
Yes.
And this doesn't really play well with our current build system and our workflow. I was wondering if this could potentially become a way to disaggregate and decouple my application and drivers from, you know, a binary that encapsulates all the Zephyr kernel and other things. Or am I taking it too far?
Yeah, I mean, I think that's like you know, a different problem. Unless you're talking about, you know, you want to segregate your application into things that you want to load and unload at runtime. I think building, you know, these things as like separate libraries that then link together at the end is a separate issue. If that makes sense, yeah.
Thank you.
Well, on the you know, on the point about setting the addresses when you flash the app, you actually have a two-way problem, right? Because if you had something on the slide there about the different user domains, I guess, or usage domains. So one of them that you want to be able to update independently is it would be like the host kernel OS, right? And so those addresses may change too.
They might.
But I think what's interesting to think about though is on some of the like the various like loadable libraries that you see in Linux and things like that, that they'll have approaches where you can at load time they might update all the addresses, or at runtime they have that special little thing. They jump off to a little function, they figure out what the address is, updates it. The second time you go through the function or the thing, it doesn't have to do that because it's already patched it or whatever. So those are like all these little interesting little tricks to consider. But I think you have to deal with the fact that once you have these loadable modules, you're going to be in a situation where you also want to be able to load anything in there and be able to fix up any of the addresses.
I think you're right. Yeah, and it could be like, again, it's a framework or a toolkit to build on top of or change to suit your particular needs, right? I work at Intel, so I've tried to focus on Intel problems in this, and that's I'm very happy to see outside contributors because it does sort of expand the use case. But absolutely, yeah. I mean, there's going to be some fun things you can do and some very tricky things you can do regarding this, right? Yeah.
So great talk. This stuff is really cool. There's a couple of questions with the extensibility, and you keep describing it as a framework from a security perspective. So I guess the first question is, like, with code signing, is it possible to patch in some sort of function where you verify before you allow the load to proceed, and then following the load finishing and the patching of every address, is it possible to have a function that you hook in afterwards to do something like reconfigure your MPU to now make that region and RAM execute only? You can't modify it.
Yeah, so I mean, really, you're entirely in control of the flow of things. So there's a function to load, but that's something that your application can call in any context it wants, right? There's a sample, the shell loader, where you can dump in a hex dump of one of these ELFs, and it'll load, and you can then call out to a symbol. But there's nothing that says that's the only flow that's there. You can absolutely check. Maybe you prefix or suffix your ELF file with an HMAC signature of some kind, right? And you go verify, hey, this is all signed by a trusted key that I know I trust it, before even trying to decode that it's an ELF file. That's totally doable. And nothing actually, today at least, nothing actually runs when you load. So the only thing that happens is we interpret the ELF file, we copy data, we do the relocations, and we provide a symbol table that your application can then find a symbol in there and call into. So if you have a particular use case where you want all of your modules to have an entry point, that's entirely up to you. You could absolutely do that. Maybe you had a macro like my cool firmware in it, right? I mean, Linux has this already sort of built into modules, but that's a particular use case for kernel modules. This is sort of like more of a toolkit in terms of like what Linux kernel modules would use, or even Linux user applications and shared libraries would use. So it's sort of the base of all of that. Yeah.
You mentioned that part of this of Lex is kind of memory management and so forth. Can you speak a little bit more to kind of what the configuration there is for someone using this on like carving out memory for the loadable modules and so forth?
Yeah, absolutely. So, I mean, today there's and it is a very simple model today. There's a single heap, right? So there's a K config. It's a dedicated heap to Lex, but there's a single heap. You set the size in kilobytes, and it is kilobytes because, as soon as you talk about enabling the MPU or MMU, you're going to use some space just simply for as in the last talk, if you were here for that, there's going to be padding for pages or MPU alignment. So it does need to be somewhat sized to account for the various sections that are going to need to be allocated there. But in effect, yeah, there's a single heap. There's also an option, and the SoundOpen firmware does use this, where not all memory has to be allocated. So you don't have to allocate all sections from the extension. If you know that your extension already lives in some addressable memory that you can already do these sorts of like permission setting bits and so on. Yeah.
All right, I'm gonna ask you about CHRE.
Yeah.
Android's Context Hub runtime environment, and how that differs from the solution.
Yeah, absolutely. So in fact, just to clarify, like some sources of inspiration that I took for this, one of them was CHRE. I did look at that. I looked at Linux kernel modules. I looked at quite a few things. I looked at some linkers because it turns out you need to actually do linking as well. But CHRE does kind of a subset of what this does. So it has a fixed symbol table for that. So CHRE is a sort of a subset of what this does, right? There's a fixed symbol table that it provides to I think it's nano apps in this case, right? But in effect, it's kind of doing all of the same things. It doesn't do necessarily the memory bit permission setting that I believe. You can double check that, Keith, if you want. I don't believe it does, but Otherwise, yeah, it kind of does the same song and dance in a lot of ways, but in a very specific way.
Hey, thanks for your talk. I'm actually giving a talk on WebAssembly later today, and there's a good amount of differences between what you're doing there and the extension models here. But I was curious if you looked into that at all, and what you see as some of like the pros and cons versus the different approaches.
Yeah, absolutely. I had someone ask me exactly about WebAssembly and using this, so it was kind of an interesting. So they were using both this loadable module and WebAssembly. And we kind of talked a bit about, what were the downsides of WebAssembly in this case. I mean, the main con that's sort of kept that's replaying in my mind is that you don't necessarily have, at least as I understood it today, all the hardware acceleration extensions or even necessarily all of the kind of one-to-one hardware instruction mapping, right? So I mean, there's part of that, but there's also there's some overhead, and you have effectively a runtime. This has no runtime. This is you're building for that target. It's and it won't run. WebAssembly has I would say that the one benefit of being portable across architectures. This is not. You're building for this architecture. You can use all the instructions available to you, all the hardware acceleration available to you.
You mentioned kind of how we have this export symbol. Is there something like, are kernel symbols exported by default, or do we have to go change everything, or kind of?
Yeah, so I mean, so far export symbol has been added sort of as needed by tests and users. Part of that EDK PR, or actually that was a previous PR, I believe, right, Ederson, where Ederson went and added as part of, so anytime I believe the syscall macro is there, it's already exported for you. So a large number of Zephyr APIs are already exported. I believe Giannotti added a lot of the libc symbols, so you don't necessarily have to statically compile your libc along with your extension. You can use the base firmware's libc functionality. But yeah, it sort of comes as needed basis. There's possibilities, so I didn't really talk about that either, but there's the possibility that maybe you want to limit what symbols are available to an extension, and there is that possibility to go manipulate that part of your ELF file at some point in your build step, right, where I only want to supply like a subset of functionality to extensions to be more in line with a plugin type system. But yeah, today it's sort of as needed, and if you need more, feel free to send a PR or just add them to your application. So yeah.
Any more questions for Tom? Oh, yeah, there's one.
I think in your presentation you said maybe drivers, question marks.
Yes, yes. So I'm glad you're asking about that. I mean,
yeah, I just did you already look at the DTS problem? Because the DTS, you have all your hardware. So now if you want to add drivers dynamically, maybe you won't be in the DTS. So did you already look at that, or?
Yeah, so I haven't looked at it too deep, and that's kind of why there's a question mark there. But I think, like, again, we go back a couple talks, right? Ederson has a great talk about deferred initialization, and I think there's a possibility there to sort of combine extensions and deferred initialization to be a little more than just, hey, don't run my init function right away, but possibly, when you run your init function, maybe that goes off somewhere and loads a module possibly. But no, I haven't looked too deeply at it. It's something that I'd happily accept a PR for if anyone's interested.
Yeah, sure.
All right. Anything more? All right. Thanks a lot, Tom.
Yep.
Great talk.
Absolutely. Thank you.
All right. Yep. Not super loud. Sound is okay? Welcome. Almost the end of the conference. I hope you all had a great week. Thanks for joining. Hopefully this should be fun. The idea is to talk about something I did a couple of years back, actually, beginning of the pandemic, but it's been a long journey, and I want to share a bit about this journey, how I basically ended up building some kind of artificial nose using really low-cost, low-tech kind of technology, initially starting with Arduino, and that was a great experience, and then I ended up eventually migrating to Zephyr, and that was even better. For those who don't know me, I'm Benjamin. I'm a developer advocate for the Zephyr project, and I'm French, so I do like baking, among other things. I do like yummy food, and I've been trying to perfect my bread recipe for the probably past 30 years, actually, and I'm still not incredibly happy about how the bread turns out. It's never crispy enough. It's never like risen enough. It's hard. I mean, some of you might be recognizing what I'm telling here. So back in, I remember like 2019 or 2020, when was the first few months of the pandemic, everyone stuck at home. I was like, okay, this might be a good opportunity, just like pretty much billions of people in the world. This might be a great opportunity to bake even more bread and try to improve my recipe. And I was like, hey, this is maybe finally an excuse for me to do some machine learning. I'm just like probably pretty much everyone in the room. I'm supposed to be a software engineer by training, except that I'm really bad at all things math. And whenever I would open a book where it's like, oh yeah, neural networks, it's easy. Look at those handwritten digits. We're going to do like matrix like feature extraction, layers, whatever. It was just, I couldn't really understand how to make anything useful out of what the book was trying to tell me. Except that, well, at that time, and now you're hearing that more and more, and Jordan was talking about it yesterday, and there's this notion of TinyML, which, by the way, that's not the name of a product. It's just the name of an approach, which is taking all things machine learning and neural networks and whatnot, and making it fit and run on small devices, with like the main idea being, I mean, you want it to be efficient when it comes to processing power, but maybe even more importantly in terms of energy. Like you want to build devices that are battery powered and that are smarter. And I was like, okay, it looks like this would be the kind of thing that I would run on those kind of Arduino devices that I'm very familiar with, and maybe this will be a way to, rather than looking at bitmaps and like pixels in something like quite abstract, like the handwritten digits, maybe this will be a way for me to look at more like tangible things, quantities, and correlate things like my intuition was telling me, things like, okay, I have a sourdough starter, I'm sort of like eyeballing it, I'm smelling it to figure out whether it looks like it's ripe and perfectly fermented or not. Maybe the machine would be able to do the same, right? And I would basically smell using gas sensors, smell the sourdough starter, bake the bread, figure out whether the bread is like a 1 out of 10, 8 out of 10 kind of bread, and then rinse and repeat and have some kind of like training material, and like maybe that was finally my way to dive into TinyML. And thanks to, again, Arduino and like the super awesome ecosystem of libraries for like sensor drivers and like graphical user interfaces and whatnot, and other tools out there. Some of you might be familiar with Edge Impulse. It's, by the way, a plug of their solution, but it's basically tooling on top of TensorFlow Lite and like a really nice, basically web interface where you start feeding your data and it's like very visual, and you start labeling your data sets. You still know nothing about the math behind it, but at least you're able to train a model and do something useful in the form of just spitting out an Arduino library that you can easily reuse. And I ended up building in literally a couple hours, minus the fancy enclosure that came later, but in literally hours, just like, I mean, the Arduino way, frankly, I put some pieces together and I was able to smell a few things. So didn't start with bread actually, because it would have taken, I guess, many, many hours or days to get enough training. I rather basically took what I had in my shelves, spirit and coffee and whatnot, smelled using a gas sensor, and we will talk about it a little more in a while, smelled and captured some data and used that for basically training a model that could then recognize things. So that was fun, and that was like, I'm by no means sort of like trying to brag when saying it took me only a couple hours. It's actually quite the opposite. Like, I really felt that I had, well, finally learned a few things about TinyML, but surely many people before me would have done the same. Like, it was a crappy, quite frankly, sensor, a very simple model, and sure, I was smelling things, but yeah, that's what ML does. But people were, like, when I started to talk about it on Twitter and social media and whatnot, people were like really impressed. Maybe, I guess, the funny enclosure helped a bit. I think I have it in my bag, actually. Do I? Yeah, whatever. Funny. So I also learned Blender in the process. That was also a nice excuse. But yeah, people were all about it. It ended up making the cover of Make Magazine. That kind of really didn't help my imposter syndrome there, because I really felt like it was something, if not trivial, at least nothing special. But yeah, I mean, it inspired people. And I think there's a lesson there in terms of, even before thinking TinyML, we're all like more or less embedded developers, IoT developers, however you want to call it. What I've realized, and I'm pretty sure it's still the case today, many people, including experts of the domain, like chemists and people from the food industry, etc., which I thought would know that it's possible to smell things or to measure gas concentrations using sensors, they didn't even know that. So let alone hooking up TinyML into that. People, when they think sensors, I think they think like temperature, humidity, the kind of thing that maybe they experience in their households, but there's many, many more physical things that can be measured and potentially fed into AI algorithm that I think the sort of the industry at large doesn't necessarily know about. So that's one. And yeah, it inspired people. So that was pretty cool. So it ended up being published in Make Magazine. There was this, actually I only realized a few minutes ago, this sweater that I'm wearing from Pasadena University. Yeah, there's this kid out of Los Angeles. He found the magazine. He was really sick when he was, I think, 8 years old, pretty much almost died. And turns out that doctors could never diagnose the fact that he had fungal pneumonia, because, like, I mean, it's kind of a hard disease to diagnose. Only through like X-rays, maybe you can spot it. But now that he grew up, there's been some like scientific research around the topic. It turns out that apparently you can smell the markers of the disease in someone's breath, like some. Essentially, if you smell like lemon, and I don't know what was the other kind of like essential marker, that could be a good sign. So he did something like pretty amazing with like an artificial respirator, etc., to train the data. He did that, except that he's 13 years old, is like obviously brilliant, but is no programmer, and the only code he had access to was my crappy Saturday afternoon Arduino 2,000 lines of code super loop. And so I felt kind of like really bad. And we will talk about more about why that eventually sort of led me to convert to Zephyr and try and do something more, slightly more future-proof, let's say. Quick side note on, because again, I said that there's this whole thing of people not necessarily being super familiar with all the ways we can sense the world around us. In case you're interested, and I'm no chemist or electrochemist, but basically the gas sensor that I'm using for the project is effectively a 4-in-1, like those 4 pieces of moss, effectively, that you see on the PCB. They all react to, one reacts to volatile organic compounds, the other to alcohol, carbon monoxide, and nitrogen dioxide. And the way it works is that there's they're being heated up, and due to the actually heated up really warm, which means also that you have lots of power. It draws a lot of current, but when it gets really hot, it starts reacting with the chemical compounds in the air, and there's some kind of like redox reaction happening, and so you can measure basically a change in resistance, which that of course MCUs are pretty good at. And so say you have 10 parts per million of VOCs, maybe your sensor will register at 100 ohms, and you have 10 times more, the resistance will be twice as big, whatever. This is where, like, when, I mean, I knew that I wanted to sense and smell data, and my intuition really, and this is where also, by the way, the tools like Edge Impulse, and I'm sure there's many others, this is where I was able to sort of finally bridge this gap I was having when reading the books. They were like, oh yeah, a handwritten digit, it's easy, it's 20 by 20 pixel, and you have like matrices. Yeah, no, I don't care about matrices. I'd rather like sort of see and feel the data. And so if I were to smell, say, whiskey here, I could look at the data and be like, oh yeah, okay, I know. If I were to write this as actual code, I would probably figure out something like, if nitrogen dioxide is going up in a steady way, if carbon monoxide is kind of flat but kind of fluctuating as well, this is whiskey. And so this, among other things, allowed me to finally, I guess, understand things like feature extraction. In this case, it's really basic statistics, looking at things like, on a given time window, what's the minimum, the maximum, the standard deviation, the average of each and every quantity, because those are going to be the sort of like the very, like the bare minimum kind of inputs that I want to feed into my algorithm, which effectively is like just, I need to solve an equation where if I feed you with the average level of VOCs, the maximum level of VOCs, etc., and I tell you that this is effectively ambient air or whiskey, please like remember that so that later on, like, I mean, training a model basically. So yeah, and the model, by the way, is really like that. Like there's no like convolution or no like, there's not much. And you could do like basic clustering probably at the end of the day, but yeah, that's it. And so that was pretty fun to build. Arduino, again, I told you, like, was really fun, or was it? Because there's actually a lot of things that's going on in there. Just like if you've been playing with Arduinos, I think, again, you know what I'm talking about. You keep adding and adding stuff, and like it does a lot of things. There's a hardware interaction with the sensors, obviously. There is a fan that can draw some, like the smells into the contraption. Graphical user interface, ideally, you make it like battery powered, connecting to the Wi-Fi. We're going to talk about some of the potentially IoT use cases behind things like an artificial nose. But if you start building that in a la Arduino, then you might be in trouble, because you've been training a model where you have like training data, which is effectively, in my case, only like sampling gas sensor data at 10 hertz for a couple seconds. That's actually enough to capture the minimum, average, maximum, etc. I was referring to earlier, which effectively represents the fingerprint, if you will, of a smell. But like the fact that the data is acquired at exactly 10 hertz, that's actually quite important. Otherwise, you get your model giving you completely bogus outputs. So in the loop, one thing that I do is acquiring the sensor data. That's pretty fast, and like I can do that. I can feed it to TensorFlow Lite for microcontrollers to actually run my inference. For what it's worth, that's also really fast. Like it only takes like really a couple milliseconds on the 200 megahertz Atmel Cortex M4, I think, chip, M4F. So that's still fast. Then there might be some kind of UI interactions. There's a UI that I need to refresh, which again, hopefully takes, I don't know, tens of milliseconds. But then I might actually want to send data to a server, and that might take a long time, and then my loop is all effed up, and I'm not able to sample the data at 10 hertz anymore, which, I mean, yeah, there's probably ways to still do that in a kind of super loop and like have some kind of basic scheduler and still stick to the Arduino way. But what I realized is that, I mean, I'd rather migrate my code to Zephyr. Actually, I should have removed the slide that introduces Zephyr. I don't think it requires an introduction, but yeah, I want to sort of walk you through some of the things, some of the concepts, subsystems in Zephyr that actually proved quite useful, because that makes the code and the application in general so much fun, actually, to work with. Things like sensor data acquisition, like it's something that can now happen in a completely dedicated thread, and I can make sure that, yes, it's going to run at exactly 10 hertz. I can have also an abstraction of the like the underlying actual sensor that I'm using. The only thing my model cares about is reading gas concentrations. It doesn't really matter whether it's a Bosch sensor or whether it's the sensor from Seed Studio that I've been using initially. So that's pretty nice. It also makes it, like the sensor subsystem, makes it quite easy to simulate the data, emulate or simulate, however you want to call it, which can be useful. There's power management integrated in it, like Jordan, again, I guess, mentioned, among others, today. This one has a small caveat, which is that the technology for the gas sensors requires, like I mentioned, for the sensor to be really, really warm. So not only does it draw a lot of current, but you're kind of stuck with it because it takes a long time to stabilize. So it's not like you can go to sleep, turn off the sensor, and then turn it on and get a reading in the next second or so. You need to wait minutes, usually, for the readings to stabilize. So in theory, you could hook up power management, but it can be tricky. Yeah, and then feeding the data to TensorFlow Lite. So a couple things to say there. One is TensorFlow Lite for micros is like already available in Zephyr as a module. So like pooling it in your system, getting automatically CMCs, DSP, and CMCs, and then potentially to kick in, that's there. So you have like great acceleration, etc. And in my case, one thing that also was quite interesting was that I'm by no means a great embedded developer, but I'd like to think that I know how to write apps in general. And so I want to write my artificial nose just like I would be writing like a regular, I don't know, web application or something like at a really high level, right? I don't really care about the really low level stuff. So in my head, like I want to be able to do something like sensor task, sensor thread does its stuff, and makes the data available to the rest of the system. Similarly, the inference thread, which should hopefully run with a much lower priority and like be when it can, does the same. Subscribes to any hypothetical sensor readings and then posts, publishes, whatever, the results. And then there's a GUI that subscribes maybe to both. That needs to visualize and display sensor data as well as the inference results. And so I've been basically building on top of ZBus for doing just that. And so then there's the GUI that comes into play. It was really, really ugly in the past with the Arduino version, using basically manipulating pixels almost directly with some kind of abstraction. But I mean, it's really fun initially, but then when you want to look, when you want to make something look pretty and don't not eat up lots of memory, etc., then it's not fun anymore. So there is a really good integration in Zephyr for the LVGL graphical toolkit, graphical framework. We have a really like super passionate and productive maintainer there who really keeps track of the upstream LVGL project. So you have basically the same LVGL as everyone else, which basically allows you, again, to my point of myself being more an app developer, I write a GUI using like widgets and like callbacks on my buttons, etc. My buttons, they can actually be buttons as per the Zephyr input subsystem, or the touch screen is effectively like, as long as I have a touch screen driver and I've hooked it up properly in my device tree, then I can start using it in my GUI. And when I start like dragging sliders around, etc., it will just work. Memory management, similarly, you can like leverage the memory attributes and whatnot to really fine-tune the way memory is going to be managed. And one thing that's also really, really cool, it's not necessarily like LVGL specific, frankly. It's more about the native simulator infrastructure that we have in Zephyr. On top of your like Linux box, your Linux desktop machine, you can actually run your app, potentially with simulated sensors, like I mentioned before, and simulated display as well. Like the screenshot you have here is the same app that's running on my actual device here, except that it's on my desktop. So like the sort of the round trip time for prototyping, troubleshooting is way faster that way. And putting all the pieces together, ML inference, ZBus, display, like LVGL display, literally the code, like again, the app code looks a bit like this. Like I have, I'm using like the ZBus macro that allows me to listen to particular messages, and as soon as such a message is being posted, then I get it and do whatever I want with it, which in my case would be calling whatever LVGL API allows me to create a fancy GUI, displaying a label, feeding data into a chart, you name it. And so we can actually probably see that in action now. Running the demo on an M5 stack ESP32 device. So obviously, I mean, you know that, but it's good to say it out loud. The app is very portable. So I have this guy that I mentioned before, like originally the Wii terminal that I used, it's a SAMD51 Cortex M4F, same app, nothing needs to be changed. And yeah, we have a chart. You might not see it all that well, but all the horizontal lines, those are like the 4 channels, the 4 gas sensors, and it says that it's reading ambient noise, ambient air, not ambient noise, right now. And the sensor is right here, and I have a smelly thing right here. Let's figure out what it is. Should work, except I might not have enough hands to do it properly, but there we go, ambient. There we go. Lemon, it says that it's lemon. We see the, so yeah, there we go. It's really kicking in. So you can also tell that the sensor is not that sensitive, not that reactive. That's just the technology. It's like $20 worth of sensors. And by the way, I think like the Bosch sensor I mentioned before, it's more like around $4. So there's, I mean, different technology, but yeah, it says that it's lemon, and the gauge is saying the sort of the confidence level. So it's sort of oscillating. Yeah, I guess now it's 80% sure it's ambient. I mean, you get the idea. I haven't retrained the model recently, so it might be that the sensor is full of finger grease. It might be that the conditions here are slightly different, but the model that I used is really literally just minutes worth of data, so obviously it can probably be fine-tuned. One thing that's also part of, and was part of the initial proof of concept, I guess you could say, is trying to demonstrate that beyond the fun or silly aspect of this whole project, there's also this idea of, hey, it might actually be a very valid use case for IoT in the form of, what if I were to stick this kind of device in the restrooms of a facility, office buildings, to figure out when the air starts smelling not so nice, to send people and clean, right? And you don't want to send someone twice a day or like twice a week, whatever, to a place that doesn't necessarily require that much cleaning, right? I mean, offices, maybe people use them less post-COVID, and so having a device that you stick, like a wireless device, you stick in the ceiling of the restrooms and posts data to an IoT server, that might actually be a very valid use case. And yeah, we can talk about, it can go both ways actually, posting data, but potentially also pushing updates to the model, why not? So yeah, I mean, obviously Zephyr has a great network connectivity stack. Part of the migration process for me, and everything's on GitHub by the way, was to use MQTT to post data, like whenever there was a new inference result that's different from the previous one, then you publish to a server, and that's something that could be used again for this kind of use case that I was mentioning. And then you start tapping into things like the whole digital twins buzzword, which in fact might actually be more than just a buzzword. If you think about a company that's sort of specialized in cleaning buildings and like doing maintenance work, etc., they probably already have like a really rich information system where they manage like all their facilities, they manage the schedules of their employees, you name it, like the billing, the invoicing of the customers. So you have this like existing database, but what if you start like augmenting it, like hopefully you code that, right? Like you have devices maybe that are part of also of this same sort of knowledge graph, if you will. So let's say we have an artificial nose device, and as part of the provisioning process, whoever's going to install the device in the third floor of Tribune Tower in Chicago, they will effectively make this association, which allows, like, it's basic database stuff, if you will, but it's still worth, again, saying it out loud, I think. As soon as such a device starts sending information, like very raw information, just like it smells, then you can do whatever in your system, right? And like query the system to be like, oh, who is responsible for cleaning floor 3 of this particular building today? Oh, it's John. Oh, but he's on holiday today, so it's actually Jane that we need to text or send an email to like send them on site. So that's one of the things that this whole project, I guess, or like a use case enables. And then there's more, of course, that I was happy to be able to use as part of the migration process, things that I didn't have when using the Arduino way, all the configurability. Like if I run the device on the application on a device that has a small screen, like it's really, really easy to make my GUI code adapt accordingly. Like maybe I want to show a graph. If I'm running on a super tiny display, I will only show the smell kind of thing. And that's something that you can do like just out of the box. You have kconfigs that expose and give you access to the screen resolution, whether you have network connectivity and whatnot. Some of you know that, of course. Testing framework, like it's actually quite nice to be able to do, especially in this context where I'm starting and thinking about decoupling really all my tasks and processes. I'm doing sensing on one hand, ML inferencing on the other, and then also the GUI. Like this is really independent. ZBus in the middle. Testing that is actually way simpler, and especially with things like Twister, etc. Taps also into the whole CI story. Like anytime I, of course, do a push on the project, I can check against all the devices and the boards that I'm targeting. So that's pretty cool. And what I find even cooler, although I didn't get a chance just yet, is Zephyr keeps adding stuff that's very relevant to this project and to hopefully many more. But you've heard about, so I was saying LLXT until today, but I'll start saying LEXT. Dynamic extensions. The model, the AI model that runs the application today, as of today, it smells good air and nasty air. It turns out that maybe in a couple of years, and apparently like that's what some scientific research seems to say, there might be ways to smell COVID in the air. So maybe I will be able, with the same hardware, to have a better model that's able to spot that using LEXT. I could theoretically, over the internet, push it over over the wire or over the air to update the model on the fly. I could add geolocation to the mix. I could add more types of displays, etc., etc. So that's pretty cool. Everything, like I said, is open source on GitHub, including the 3D enclosure. Should you want to print it? Originally, I thought it was a bad design, but apparently many people around the world have been printing it, so I guess it works. The actual Zephyr-based project is this particular URL. The other one would have been the legacy project if you want to get the parts. I'm not getting anything out of that. I guess I should, because I think they've been selling quite a few, but among others, see it as like a SKU, like one click on their website, you will get the WIO terminal, the gas sensor, the baguette. No, I don't think the baguette comes with it. And yeah, that's it. I think that's what I had, frankly. We have time for questions, so I hope you have some. There's one here.
Great talk. I really liked it. So did you manage to apply your digital nose to improve your baking?
I should have a slide about that, because that's actually the first question that everyone asks. I moved on. Like I figured I had a lot of fun with the whole thing, but the thing is, and well, I actually kind of used to have a slide about that. The thing is, back in May of, again, I think it's 2020, right? Whatever, really early in the pandemic, there wasn't even flour on the shelves in the store. So I would have needed to bake dozens and dozens of baguettes, right, to train the model and eat the bread, which might have been also a problem too. But so yeah, it was way much easier to literally spend minutes smelling whiskey and coffee and whatever I had. And for what it's worth, like with a very simple model, very crappy sensor, my initial tests, like as part of this first Saturday afternoon, was with booze, like I think I mentioned. And yeah, like different kinds of whiskeys, it would be able to pick up the difference, like a really peated whiskey versus a slightly less peated one, versus vodka and rum and yet another rum, I think, like those 5 spirits, including like 2 rum, two whiskey, it worked. So that's, but yeah, no bread, never actually tried.
So now you are an alcoholic instead.
I also have one more question.
No, like the thing is that I didn't need to drink, as opposed to the bread. I might have become a celiac or whatever.
I was also wondering what your data collection process was to build up a data set to train your model.
Yeah, so and so that's actually a feature that's still in there, also that I ported from the Arduino legacy app. So there's this edge impulse thing, but it will be applicable to other sort of workflows that makes it really easy to, so the way it works is that I build the app with sort of a flag on which, when it's on, the device would dump sensor data to the UART in a CSV-like format. And then the edge impulse thingy has a daemon that runs on your machine that forwards the data to the cloud. But it doesn't have to rely on the cloud. And it makes it really, really easy to feed data in somewhere, label it. And so you can be like, OK, I want to capture 2 minutes worth of data. So it starts listening to this stream of sensor data. Then you label it, you visualize it. I think I can probably pull it up just like real quick right here. You can visualize it. It suggests you some basic DSP slash signal, slash statistics blocks that you might want to use to do the initial feature extraction. And then you're good to go. Like it's, so let's see. So that's training data. So exactly like I said, like I click, I'm like, OK, I want to capture 30 seconds worth of data that I know. Oh, I'm not sharing, sorry. Should have told me. All right, I'm not duplicating the screen, so it might be a challenge. Yeah, whatever. Yeah, that's enough. So those are all the captured samples. So 30 seconds of whiskey on May the 7th of 2021, blah, 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 blah. And then the tool automatically suggests some feature extraction things that would work well for time series data. So would you like to try to average the data on a two seconds window? Would you like to try to blah, blah, blah? And then once you have that, it does kind of the same process for suggesting some very basic, like fully connected neural networks, and then you're good to go. And then, like I said, once you're done with it, you realize that maybe there's just really little actual, very few features that actually contribute to the results, so few that maybe you could actually do the whole thing with just like an if. Like if VOC is above this threshold, it's always coffee sort of thing. But it also works with the neural network. And if you do all the optimizations, it's not necessarily going to be more costly in terms of RAM processing power, etc. So that was my long answer, I guess.
Hello. What will be the difference between this artificial nose and then air quality sensor? Because I know those are also using gas sensors.
Yeah.
Or
so
maybe you can use them at a large scale, like for air sensor.
From what I know about air quality sensors, there's an aspect to them which is they look also at particulate matter concentration. But one thing that I often tend to mention with, I mean, I call it an artificial nose. It's by no means like anywhere close to a human or a dog nose. But it's a device that smells, but in fact, it could use whatever kind of sensors. Potentially, just like we do sensor fusion with accelerometers and gyros, etc., we could think of doing the same. I mean, what I'm trying to say is, if you want to build a device that makes up the difference between orange juice, water, and wine, if you can afford or if you have access to a color sensor, maybe you can feed that also in the system, right? And then you have concentration of VOC, air quality, humidity, color. You feed all of that into your like training workflow, and then as part of the training, you will realize that, well, you know what? Only the color input is required, right? So yeah. Anthropomorphism is something that we tend to do maybe too much of for those kind of applications, I think. And yeah, it's not because it's a nose that it has to use gas sensors, I guess is what I'm saying.
Any other questions? No, I have a question. So what's the next step? Test sensor?
What's
What's
sensor?
the next step after the smell? Test? What about test? Do you have any idea? Did you think about something else to take it beyond just smelling?
Beyond just smelling, no. I would love, so a couple of things. I would love for that to help. And I was having discussions with folks around accessibility. There's lots and lots of people who suffer from anosmia. So we lost the sense of smell during COVID, or for like they've had a really bad cold and they lost their sense of smell forever. So putting the device in a fridge to figure out when the food gets spoiled. Like I actually had someone somewhere where I was sort of demonstrating this device came to me and was like, last week I kind of almost died because I ate, like I don't have the sense of smell. I ate some ham or eggs or whatever. I wasn't sure, but I ate them anyway, and then I was really, really sick. So there's that as part of the what's next. Like it would be great for someone to pick it up. It might require better sensors. It might require the sensor fusion thing that I was referring to. Maybe that could help that. And also, what I would like to see is, just like we have all those data sets for training like facial recognition algorithms and like image, video recognitions, all those labeled data sets for images. I don't think we have, I mean, I know we don't have the same for smells. And so at some point, ideally in open source, it would be great to have that. Like it comes with tons of challenges regarding how do you even represent a smell in the first place. But yeah.
Okay. Thank you, Benjamin. And
thanks.
Yeah, see you around.
Thanks. Thanks.
Maybe a follow-up would be pairing with a computer vision algorithm and try to detect who farted in the elevator.
Yeah, I've had a lot of those questions and comments too. Thank you.
I bet, yeah.
Yep.
Do you have to calibrate the sensor anyway?
Oh, yeah, that's a good question. Those sensors, they are really not that great, so you cannot even calibrate them. So you need to retrain the model with every, like,
you to give the talk. Why you thought I would mention it, or I was scared. Joking. No, I never. I mean, that's really, really cool. Now we also need to mainline all the work that we can do. And I never some other stuff that would make the portability
stuff
So you
to
got all
put it
the
in.
sensors as well, huh?
I got a couple, yeah.
So it's interesting. Oops. Wow, the connectors and everything.
Yeah.
They're like very well covered. Ford people. And you don't see the PCB, which is
Mm-hmm.
a new thing. Looks like the new style. What's that?
I don't know.
Oh, this is for the quadcopter, I think.
Mm-hmm. Oh, maybe that's for the
Yeah, this is like
propellers.
the one going in the
Yeah. I think that's a GPS.
Yeah. Wanna
Yeah.
make something new?
Yeah.
Sorry about that. Benjamin says I have to start talking. Welcome to the last day of the Embedded Open Source Summit and our Zephyr Summit. And late in the afternoon, I'm sure there are plenty of pillows to go around and lap blankets for everybody to take a nice nap this afternoon. My name is Keith Packard. I'm a senior principal and software engineer at Amazon. But you get to listen to my hobby project. So this is something I do in the evenings because I don't do enough software during the daytime, which is frighteningly true, actually. I started this project because I needed a C library for rocketry and satellite applications. I was doing embedded software with my own RTOS because everybody has to write their own RTOS. Yeah, it's kind of a requirement, right? At the time, I didn't have a C library that fit in the platforms that I was using. All the kind of the default embedded C libraries were too large for the targets that I was shooting for. I had some devices with like 32K of ROM, 32K of flash, and consuming a significant fraction of that with newlib just wasn't really an option. Let's see. PicoLibC is a C library implementing the standard C APIs and some POSIX APIs for 16 to 64-bit embedded systems. It really doesn't target 8-bit systems. It kind of runs on AVR a little bit, so who knows? Maybe some people use it on 8-bit systems. One of its chief goals here, because I do a lot of safety critical applications in space, in the area of space for satellites, we don't like things to go wrong, and we don't like unexpected execution paths to cause troubles when you're on orbit. And so I don't use malloc in any of my applications. And so the thing that I really don't want my C library doing is using malloc behind my back. And so by not actually exporting malloc at all or having any dynamic memory allocation APIs in the operating system, I can be pretty sure that malloc is not being used. So that was kind of a key requirement for me. It's tuned for small memory footprints. There are some faster code paths that you can use and add and optionally compile in, but my targets are small systems, and so I'm looking for the smallest possible memory footprint. Obviously, testability is super important in any safety critical application or pretty much any system software. And so PicoLibC has a pretty extensive integrated test suite that gets run every time any commits are added to the repository. PicoLibC focuses on both C and POSIX conformance. So the test suites check for a bunch of POSIX and standard C API conformance. And if you find a bug, well, I just got a bug yesterday where PicoLibC was returning the wrong value from FE set round when you passed it an invalid value. And that resulted in a storm of about six commits required to fix that across all architectures from one tiny little not returning the right value when you check a function. So I'm super interested in C and POSIX conformance at all levels. So error no values, the correct exception values from functions, all that kind of stuff. Super interested in making sure that all of that is correct. Because if you've got a standard and you're almost implementing the standard, you might as well not bother to implement the standard at all. Because if your users can't count on the library to actually conform to the standard and be able to read the documentation and understand what the library is doing, then they really don't have a lot of faith in the rest of the implementation either. The current PicoLibC version is 1.8.6. Their numbering is kind of random. The one basically says, oh, by the way, the API is never changing because it's got a standard behind it. Why would you ever change it? And the other two versions kind of change randomly at my whim. The API is never changing, and so we don't really have any additions or we don't have any incompatibilities ever in the library. And so, kind of the semantic versioning doesn't make all that much sense in this world. It's like it's all just minor version or kind of patch version updates at this point. This version was released on the 21st of January. One of the big additions was a tableless C-type implementation. Somebody pointed out that the C-type table was 384 bytes. And if you call a couple of is blank or is ASCII calls in your application, and that pulls in 384 bytes of a static table, it's like, wow, that's a huge amount of space. And I know everybody around here, everybody in the Linux space is kind of laughing at me. It's like, what? You're worried about that? And it's like, well, yeah. I got 4K of ROM on some of my devices. 384 bytes is huge. So the tableless C-type implementation, I've got a slide about that later. We'll talk about that. But it gets rid of the table, obviously. The other thing that 1.8.6 does is kind of normalize and regularize the use of the GNU inline semantic. The GNU inline semantic is something which allows you to declare a function inline most of the time, but also provide a version of that function in the library for external linkage. So if you happen to need a function pointer, or you happen to have an application that just doesn't happen to include the header and doesn't get the static inline version of it, you can get both. That's not part of the C standard, but it is a super common part in both Clang and GCC. And it's really valuable for being able to inline things like these C-type macros. And that's where kind of where I started with it. But now it's kind of regularized across the library. So any place there's inlines in the library, this should be available as both inlines and functions with external linkage. I added somebody actually proposed an optimization to speed up buffered fread and fwrite. And I'm like, sure, we'll throw that in, what the heck? And that lets you actually do the obvious memcopy when you're doing buffered I/O so that it's not doing a character at a time operation. So it's a bunch faster for that. More testing targets. How many of you are still using 32-bit Spark? No takers? How about Super H? Anybody excited about a Super H user? There we go. Yeah, Super H is a new supported and tested target in PicoLibC. It's the library for you. you know, you laugh about all these ancient targets, and you think, why would you bother to support a C library in that? And the reality is that every one of these compilers has quirks. Every one of them exposes new parts of the library to testing that haven't been tested before. Every one of them is an opportunity to learn something about how machines work and how compilers work and how the language works and how the library works. And so I like to test across a lot of different architectures, even ancient ones. Probably some of the most interesting work I did in the last year in PicoLibC was supporting the 68K. The 68K looks a lot like an IEEE float machine, but it's not quite IEEE float. And so all of the little variations, minor variations in math functionality required to support the 68K, that kept me occupied for weeks. It was great. Let's see. And I finished some unusual FP format code. There's a bunch of targets that vary the size of float double and long double depending upon compiler options. There's one target that I support that has that will let you use 32-bit IEEE binary for float double and long double, or just for float and double, and long double is 64 bits, and it's like, these all need to be mapped in the library automatically so that when you call a float function, you get a 32-bit float function. When you call a double function, you get the appropriate double function. And so the library now dynamically maps all of those names into the appropriate underlying implementation using symbol aliasing. So that if you have a target like, say, ARM, where double and long double are the same size, now there's zero overhead for using long doubles in that target because you get a symbol alias that dumps you into the double code, into the same code that is executed for doubles. So that was kind of fun. Okay, there are a bunch of tool chains where you can get PicoLibC for free. I know a bunch of us use Zephyr. The Zephyr SDK obviously has PicoLibC embedded in it. And that was done because PicoLibC was integrated into what Zephyr uses, which is crosstool-ng. The patches that we put into crosstool-ng actually let you select at compile time, when you're compiling your application, whether to use PicoLibC, newlib, or newlib nano. And that was changes that I made in order to make it easier to integrate PicoLibC into crosstool-ng so that people didn't have to choose when building the tool chain which C library to support. And that actually includes both C and C++ support, which is pretty cool. Question? Absolutely.
I assume you have automated tests. Do you assume fused instructions are turned on or off when you do your floating point testing?
So the question is whether I assume that fused instructions are turned on or off. The C standard says you can't use fused instructions because it gives you different answers. And so all of the math functions assume that you're not turning on the fast math fused instruction stuff unless you explicitly ask for fused multiply add instructions with those inline functions. Exactly. Clang and GCC don't turn it on by default, as far as I know. Although are people configuring it to turn them on? You get to keep both pieces when you violate the spec. Don't do that. Yeah. Oh, so one of the other fun things I got to do in the last year, actually along the same lines, was so we wanted to be able to have multiply, accumulate, and round functions in the library, right? It's a super important optimization. Well, it turns out to do multiply, accumulate, and round, I learned about the obvious technique for doing it without actually having an instruction. Use the old IBM double-double technique where you have two floating point values that add together to be the result that you want. And so your intermediate representation for your fused multiply and add is these two floating point values that add together to be the correct result. And then you can round those correctly to get the result. So you do a single round. So that was fun. Kind of a fun little diversion for an afternoon. It's like, oh, wait, I bet I could use that. Yeah. So PicoLibC now supports the multiply, accumulate, and round functions, even on hardware that doesn't have those, instructions, and it rounds correctly in all the rounding modes. So things you can do with a hobby project. So crosstool-ng is a super popular one. I recommend that for anybody who's trying to build their own tool chain. it's a really great place to get a nice tool chain. LLVM ARM is actually shipping an LLVM-based tool chain now. And that tool chain with Clang, and LLD, and PicoLibC, they use that by default now. So if you want to use a Clang tool chain, you can just go download it from ARM, and it includes PicoLibC already integrated. The GNU ARM embedded tool chain, which uses GCC, don't use that one. That one is built with thread local storage, the thread local storage capability in the compiler disabled for reasons beyond my understanding. It literally just takes away functionality from the users. It doesn't add any value to the environment. So if anybody has any pull with ARM to get them to go fix their stupid toolkit, their embedded tool chain, that would be super helpful. I ship binary add-ons to that to just lay in a PicoLibC over the top of that tool chain. So if you're stuck using that tool chain, I actually have binaries available for you to just unpack on top of the GNU ARM embedded tool chain. You can use PicoLibC. But again, just go use CrossTool or use the Zephyr SDK, which is the same. Let's see. Application build options. So you can configure PicoLibC at 2 times. You can either configure it when you're building with PicoLibC, or you can actually do a bunch of configuration, obviously, when you're building PicoLibC itself. So actually, one of the things that was super useful for Zephyr when you want to use an SDK of any kind is you don't want to have to recompile the library to take advantage of features in the library to optimize various things. A bunch of newlib, for instance, lets you select between integer and floating point printf using linker tricks. PicoLibC is the same, just a little more advanced, a little fancier. That means that all of the 2 things you can configure in PicoLibC at application build time are which printf and scanf level you're using. The reason for all of this complexity is that printf and scanf are like the big functions in are typically used by embedded applications. They're super complicated, and to fully implement printf and scanf takes an enormous amount of code. I haven't even finished with printf and scanf. I still have 128-bit and 80-bit floating point support to fix. It's not standards conformant yet. But that's a lot of code. It's like 5 or 10 kilobytes of code. Oh my God, so much code. Zephyr gives you options when you're building a Zephyr applications of how much CB printf support you want. And because when you're using PicoLibC, CB printf is supported by printf, that kind of falls back to also offering how much printf support there is. And they kind of go together. And there's kind of 4 levels in Zephyr right now. There is an integer-only mode, which only prints out ints. It doesn't print longs. It just prints ints and strings, but it does all the formatting stuff. There's a long mode, a long mode that also takes long longs, so 64-bit values on ARM32, and prints those out. And then there's a floating point mode that prints out floating point numbers as well. And so those are the kind of and there's a minimal mode in Zephyr as well that is like a cut down version of printf that doesn't support a lot of the fancier formatting stuff. And PicoLibC has that as well. So PicoLibC kind of maps the Zephyr printf modes and CB printf modes into its own printf modes. And those are actually available with the SDK using the binary version of the library. And it does that with linker tricks. The other thing you can configure at build time is which C-type you're using. Because the C-type stuff is super easy. It's either static inline functions or static inline functions that do direct value comparisons, or static inline functions that go look up stuff in arrays. Then you can actually just, it's the code that gets put into your application is static inline stuff, so it's all done at application build time. So you can pick which of those you want. By default, if you're compiling optimized for size, you get the newer C-type stuff that's just all static inlines with direct comparisons. If you're compiling for speed, then you get the table-driven version. So some of this stuff PicoLibC can kind of do automatically. When you're building the library, there's a lot more options. There's so many options, pages and pages of options. These are kind of the big areas. The biggest area is locale, language, and character set support. I still don't really know what I want to do with this. There is an enormous amount of non-Unicode character set support in PicoLibC that inherited from newlib. It supports a bunch of GIS encodings. It supports all the Microsoft code pages. It has a bunch of ISO support for all the ISO 8859 encodings. And I'm like, does anybody use that? Is that even interesting to anybody? You know, does anybody use the code page translation functions that are in the library? It's like, I don't think they cause a lot of bloat in typical applications, so I haven't removed them yet. And then there's language and locale support. The locale support in picolibc is pretty thin. It supports the C locale, because we all love the C locale, right? Yeah, which made it super easy when somebody asked me if I could add the option to have commas between the groups when you're doing printf, to put commas between every 3 decimal points. And I'm like, absolutely, that's super easy, because in the C locale, the separator there is the empty string. So in the C locale, you don't get commas. So all I have to do when I see that option in the printf string is ignore it. Very simple. Obviously, there's a bunch of standard I/O options. There's even more printf and scanf configuration bits. You can turn on and off whether it supports the new binary output thing. You can tell whether it supports the POSIX positional parameters, all that kind of stuff. The fast buff I/O is selectable. It's usually on by default because it's only used when you're using buffered I/O. And then there's the big option. There's actually a whole separate legacy standard I/O implementation from NewLib. I haven't deleted it yet. It used to be there because the tiny standard I/O that picolibc added didn't do everything. But at this point, the tiny standard I/O is actually more standards compliant than the legacy standard I/O. The legacy standard I/O is a ton faster though, because it's only buffered I/O. It doesn't support unbuffered I/O like the tiny standard I/O stuff. So I don't know if I should remove it or not, because I can imagine some people really need the performance of super fast standard I/O, or they want to be able to take advantage of the libstd and C++ standard buffered versions. I don't know. Maybe there's some reasons. So there's a whole pile of code just sitting there. It's like, I don't think anybody's using this. For the math library, there's a couple of interesting options here. Normally, picolibc is built in just IEEE mode. And in IEEE mode, all the math functions only set exception flags. So if you do a divide by 0 or an overflow or an underflow or any of those invalid operations or exception generating options in the math library, by default picolibc just sets the exception flags and moves on. So if you're running a soft float environment where you don't have any exception flags because there's no register to stick them in, you don't get any indication of an error at all. There is error no support in the library, and you can conditionally compile it in. It isn't compiled in by default for most of the builds that I do, because it adds a bunch of code, and almost more importantly, it adds a dependency on errno that you probably don't want. Errno is one of those, things from the distant past that were like, why did you pass error status back from the operating system in a global variable? What were you thinking? So, Zephyr has errno support, and it's all per thread, as it should be. And you could use that errno support in picolibc, and it works if you enable it. But I kind of like the IEEE exception mode better than the errno stuff, so that's what's turned on by default. There's also some new floating point code that was added like 5 or 6 years ago. ARM shipped a bunch of better math functions for things like sine and cosine. The problem with that code is that the 32-bit floating point primitives are implemented in terms of 64-bit floating point operations. So if you call the sine function with this code, it takes your 32-bit value, expands it to 64 bits, does some 64-bit math, and then packs it back up in a 32-bit value and hands it back to you. And if you're on a machine where 32-bit and 64-bit floating point operations are the same speed, like every ARM machine, every 32-bit ARM I've ever visited, oh wait, not that. But there are a bunch of machines where 64-bit operations are the same speed as 32 bits. taking advantage of the additional precision makes things go faster because you do fewer operations to get the desired precision. You don't have to do so much fiddly extra fix-ups to get those last few bits done. The problem is that all of my targets, and I suspect most of your targets, are like Cortex-M4. That only has 32-bit floats. And so if you use the new ARM code on that target, oh, wait, now we're going to go do soft floating point for these primitives. So I don't know why that code was pulled into newlib from ARM. I don't know what it's for. I don't know what ARM target is interesting to use with that code. But it's still there, and you can ask for it, but it's not used by default. It's also less accurate. New code, less accurate. The mysteries of the universe. OK. So this is a new change. The old C-type code is obviously kind of the classic design. The reason the C-type code was implemented this way is super simple. It's really small per use, but almost more importantly, it's table-driven, and so you could use C preprocessor macros and not evaluate the parameter multiple times. And back in the pre-NC, pre-inline days, you really had to have that as the implementation. You couldn't evaluate the parameter multiple times because a lot of people do, while is blank of star B plus plus. And if you evaluated that parameter multiple times, you would completely wreck the code. And so they used the table-driven mechanism to be able to reliably evaluate the parameter exactly once. The table is at least 256 bytes. At least, I say. Because signed char is a constant problem. I just learned earlier this morning that the Linux kernel now makes sure that chars are always unsigned. They actually force char to be unsigned on all platforms so that the code is the same across everything. And so you don't get variations across platforms. I think that's an interesting question for the Zephyr community. Should we do that too? Should we adopt, because on ARM, chars are unsigned. And on x86, chars are signed. And it's like most people often use chars with 8-bit values, assuming that it's an 8-bit value, and they're not expecting negative values. So from a consistency perspective, I think there's a lot of value to be gained from thinking about that. To support signed chars with this old C-type code, this is great. They actually have a 384-byte array. That's actually 385 bytes. And they take the character value, add 1, and index into this array, which is offset 128 bytes into the actual start of the data. So that if you have a negative value, it goes backwards and pulls out the correct C-type information. It's like, that's a cute hack. Yeah. C-type, by the way, is not defined to operate on negative values. It's designed to operate on unsigned characters or EOF, -1 for EOF. So that is an invalid usage of C-type, and yet the new lib code that PicoLibC inherited is like, yeah, but people do invalid things all the time. Let's protect them. I applaud that. That's definitely the right plan. The old C-type code supported all the 8859 code pages. All the 8859 encodings and all of the Microsoft code pages, but it didn't have any Unicode support. I don't know why. One of those mysteries. It has lots of tables, but it was like missing the obvious tables for Unicode. And so it's got value because if you're doing different encodings, that's the only way to get different encodings because in different locales, because it can actually switch which table you use based upon the locale. And so the table-driven stuff can actually go fetch the table out of the locale and look up the value from the table, and all that's relatively straightforward. With direct comparison mechanisms, there's just no way you could support multiple locales. So the old code is still useful if you're using locales. The new C-type code is the obvious implementation, right? It's just using inlines. You have static inlines that just directly compare the provided character value against the appropriate ranges. It has a nice integer declaration for its parameter because that's the correct declaration. And it means that all the problems with negative values, that all evaporates because we're just doing comparisons on values, so all of them work correctly. It only works in ASCII, C locale. We love that. It uses GNU inline, which is a semantic supported in GCC and Clang, not supported in some other compilers. So if you're using other compilers, all of the inlines evaporate and you're doing external linkage functions for all of these operations, which kind of sucks. It's selectable at application build time, and if you compile for size optimization, you get this stuff by default, and you get the table-driven stuff if you're compiling for speed, because it is a lot faster. Or if you want to actually statically declare which one you use, you can just define this variable before you include c.h, and you get whatever you ask for. Pretty simple. Let's see. Floating point fun. This is I was talking about the new sizes, and this is a deeper explanation of that. So C defines float, double, and long double, but it doesn't tell you what they are. We love C. It's our favorite language. It's great, isn't it? Machines that picalibc supports support all of these different types. Oh, and there's extra ones here that I didn't list. So 32-bit, 64-bit, and 128-bit IEEE binary, 80-bit IEEE extended, 128-bit double-double. It's got very limited support for those. And it also supports the 80-bit M68K types as well, which are not quite IEEE, and the M68K 64 and 32-bit types, which are derived from their 80-bit types. Compilers are free to map them however they like. Most compilers have a static mapping. I think with the ARM compiler you can actually tell it. I think you can probably tell it that you want doubles to be 32 bits. There's probably a GCC option for that, because I know there is for AVR, for instance. You can tell AVR to make doubles be 32 bits. Super convenient. And so now all the math library code in picalibc is it's got, well, the 32-bit code is always assumed to be float. And then the 64-bit code is either double or long double or not used at all. It's never float, fortunately, not so far. And so the 64-bit code has to kind of switch between being the long double code and the double code. And so it's all this hairy parametric function names and macros everywhere to make sure that you land in the correct function when you have a double data type, whether it lands in the 32-bit code or the 64-bit code. Right, and I mentioned there I'm using symbol aliasing, so it's free. Symbol aliasing is there's kind of like two different ways to do it, and the newlib had used this old technique where it actually used inline ASM in the source code to do the aliasing. It actually had an inline ASM that had a .equ in it to do the aliasing. I'm using the attributes now and the GCC pragmas to get the aliasing to work correctly. That fixes a bunch of problems on systems that prepend underscores to their symbols. Thank you. What system was that? There's some embedded target for which the ABI still prefixes underscore on global symbols. Thank you. I don't remember which one. Might have been Spark. I don't know. One of those. Using the compiler is obviously the right way to do that, because then the compiler sorts it out instead of having to sort it out myself. So at this point, picalibc has pretty complete support for all four of those data types, 32, 64, 80, and 128. It has a tiny amount of support for double-double. Anybody know? Anybody experienced the delights of IBM double-double? Yeah, it's a wacky representation. So this was IBM's plan to do extended precision math. It's basically you take two floating point values, and the real value is the sum of these two, and the rule is that the exponent for the right side one has to not, the significand doesn't overlap at all. You make sure that there's no overlap in significand, and so you shift stuff around to make sure that they don't overlap, and that they sum together to be the actual answer. And there's pretty straightforward rules for doing addition and multiplication and subtraction on those. And it all kind of works, except that you have this weird variable precision because the smaller exponent may be way over here. And so it's really hard to understand what it means to do rounding or to do what's the error value of this function. It's like you have variable precision. Not my favorite, but PowerPC uses this by default. Oh. Yeah. So there's a tiny amount of support for that in picolibc. Pretty much, it's got rounding functions and classification functions like isinf and isnan and that kind of stuff. And it has square root, because square root wasn't too bad. But don't ask me to do any of the more complicated intrinsics. Let's see. They're mapped at library build time and uses simple aliases. I should review my slides before I give a presentation, shouldn't I? A lot of this stuff was for AVR. AVR pretends to be a 16-bit platform. It's really an 8-bit platform, but it pretends to be 16 bits. And somebody got excited and came in and said, can we use picolibc on AVR? It's like, AVR has a pretty good C library. It's really small, nice for your tiny targets. And they're like, yeah, but we want to use and I got a bunch of patches. And I'm like, okay, your name is not Jiantan? Good to go. That joke's not going to get old for a while, is it? Yeah. Let's see. Okay, so one of the biggest motivating factor for me actually doing a bunch of work in the C library was standard I/O. I struggled with trying to find a competent standard I/O for my embedded systems forever. The number one thing is it has to be standards conformance. Printf is freaking hard to implement. And it's got a lot of options and a lot of niggly details. And applications depend upon it doing what it says on the tin way more than they should. Because there's a lot of corner cases here that you can get wrong really easily. Obviously, I want to avoid malloc because my systems aren't going to ship with malloc because when malloc fails on orbit, what do you do? Yeah, actually, you don't even crash because you're still in orbit. You just kind of go quiescent and die. And it's like, oh, more space junk. Great. Yeah. So I found this awesome algorithm, the Ryu floating point printf algorithm. It is standards compliant. It is not the same as what most printf implementations do. Most printf implementations, to be standards compliant, use arbitrary precision arithmetic in the middle of printf. With mallocs, the whole 9 yards. So you're printing a floating point number. It's like, oh, we're going to go malloc a giant pile of memory and do some arbitrary precision arithmetic for 10 minutes. This algorithm is all fixed precision, but it is standards conformant. And by standards conformant, I mean that if you print a value, you get a value which is the closest possible decimal representation in the number of digits the maximum number of digits that it can present. And then when you read that value back in, you get exactly the same bits you had before. So it's round trippable. And that's kind of the most important attribute of that. It does not give you if you ask for 100 floating point digits, glibc will actually keep printing digits all the way out to the 100th digit, getting closer and closer to the decimal value of your floating point number. This code doesn't do that. It's like, yeah, we're going to print out 17 digits that is enough to represent the value, and then you get as many zeros as you asked for. Standards compliant, does what it needs to do, and doesn't have to do arbitrary precision computations. Let's see. We only got about 4 minutes left. I think I'm going to skip some of this stuff. I talked about the buffering. So picolibc uses a buffer-free API. It means it has getchar and putchar for every single character in and out of the library. That's super slow. One of the cases that I've discovered that is really common for people to be using this for is SN printf just with %s. And the reason that people use SNPrintf with %s is they don't want to use strncopy. They replace strncopy with that. Why would they do that? Anybody know why they would replace strncopy with SNPrintf? No, the reason you replace strncopy with SNPrintf is SNPrintf guarantees the result will be null terminated. strncopy does not. So it's a nice fix for a library bug. We have better fixes available, but that's a really common paradigm that I've seen. And using picolibc for that it sucks. It's really, really slow. The other problem with standard I/O is that the size of the file struct, it varies depending upon which kind of file struct you're using. And that's kind of problematic. It means that you can't use freopen with things like standard in. I don't know how to fix that and still meet my memory budgets, so maybe it won't get fixed. Let me see. I think I can see, oh my goodness. I'm going to talk about some Zephyr stuff. Picolibc is now the default library for Zephyr, so if you're using the defaults these days or you're using Zephyr head, you'll be using picolibc. You can either use picolibc out of the Zephyr toolchain, the Zephyr SDK, or you can use it out of a picolibc module and actually build the library at the same time you're building the application. You need to use the toolchain version if you're using C++ because the toolchain has to be compiled against the ABI of the library, and so you can't use the module version of picolibc. So there's a bunch of options you don't get in customizing picolibc. You can't get if you're using C++. But after I added the printf stuff to make sure that you could, customize printf, most of the need for that went away. So it's pretty cool. You can actually use C++ and libstd C++ and picolibc in your Zephyr applications. It all works just fine. And here's a couple of examples of how to build it and how to run an example. To configure stuff with Zephyr, you can configure the printf and scanf level. Those are automatically configured by your CB printf stuff, or you can go in and customize them in the picolibc bits. You can also set the malloc heap size. I may have made a mistake here in the default configuration. Picolibc uses the same malloc that the minimal C library does now. Exactly the same code. The only difference is that when you select picolibc, the default heap size is different, and that's probably a mistake. With the minimal C library, the default heap size is 0. So you don't actually have a malloc heap. I don't know why it's 0, but it is 0. And with picolibc wanted to make it useful. It's like, well, why don't we just use all of the available RAM that isn't used by anything else for the malloc heap? It's pretty easy to compute. Well, it didn't turn out to be that easy to compute. And it causes some occasional linker adventures. So probably not the best possible plan. Maybe we should switch it back, but maybe it's too late now. If you want to customize picolibc at a finer level of detail than is provided by the C-type and printf stuff, you can go in and use the module, and it's got half a dozen options. It's not as customizable as the upstream picolibc configuration because there's a bunch of stuff that just doesn't make sense for Zephyr. So it's pretty limited in that way. But yeah, how many of you have actually discovered that you're using picolibc when using Zephyr? Yeah, a bunch of people. Very cool. Very cool. I'm going to end here, leave a little bit of time for questions. And thanks so much for coming this afternoon. I know it's late in the afternoon on the last day, and what we all want to do is go get some dinner and go to bed. Oh, wait, maybe some people want to do other things, but that's my plan. I have a microphone if anybody has questions. Oh, more microphones.
Right. So my intuition with alternative car sets, like things beyond, is that it would take a fair amount of space. But you mentioned that it wasn't that big actually to support the alternative car sets.
So by alternative character sets, I mean things like the Microsoft code pages and ISO 8859-N. Those are both byte encodings, and so their tables are 256 bytes or 384 bytes in the case in the picolibc case. So they're not huge. Now, if you ask for the GIS character encodings, those tables are enormous. They take like 30 or 40 kilobytes to do just to Unicode mapping and back. So they're pretty expensive. You have to ask for them, and they're not available by default. And you don't get them, of course, until you call the functions that need them. So we could build them into the library and make them available and just never use them. And it's pretty inexpensive. What gets expensive is when you add the locale support and all of the standard C functions that used to just have direct inline stuff now have to go out and check to see what's up with the locale. And the NewLib has support for locales, but the only real locale support it has is when it's being used in Cygwin. So it has acres of locale support, none of which work in anything but Cygwin. So all the embedded targets for NewLib just get the C locale. But it still has all this locale code and all this locale conditional stuff. I need to kind of figure out what makes sense to keep using in picolibc. It's still kind of, I haven't spent the time to kind of figure out what locales mean in an embedded environment. So you can have character sets without locales, but a lot of the usage of character sets is tied to locales.
May I also have a question, or? Yeah. First, Keith, thank you so much for all this work. Quite amazing for hobby projects. Somebody do that full time and do much less. No, seriously. So what is behind the corner or around the corner? So what do you plan for next months, years, or you don't have any plans?
I don't really have a lot of plans going forward. I'm watching, right now, Synopsys is doing a bunch of evaluation with a proprietary C library test suite that they have access to. I'm expecting to see a lot of bugs coming out of that, which is super exciting. Bugs are good. Bugs mean you're finding problems. So I'm excited about actually getting bug fixes for those and adding tests that uncover those bugs. As I said, I still have some printf and scanf support for really long floating point values that I need to add. Right now they're approximated. They're not round tripping. They're just doing the old school floating point math to kind of try to generate approximate digits. So I've needed that to do. Other than that, I have a PR submitted on Zephyr right now to fix the fact that the malloc heap is always included in every application. So I'd love to get some review on that. I think it's one of 2 outstanding PRs I have in Zephyr. So if anybody wants to review my PR, I'd love to have that get reviewed. But in picolibc, I don't know. Anybody have any? I have a bunch of stuff I would love to do, but kind of my biggest project is something that's really big. I want to go rewrite the math library. The math library has a bunch of precision gaps that have been uncovered over time, and it would be nice to actually go in and fix it. One of the nice things we have with modern computers is that we can actually enumerate all 32-bit floating point numbers and run them through functions and evaluate, exactly how precise all the math functions are. And somebody has done that and actually has numbers about picolibc precision. Which is how we discovered that the ARM functions were less accurate than the old Sun functions. And so I would love to go in and rewrite all that stuff. That's a really big project because I need to actually do the math to understand how those polynomials are generated. I've read about a dozen articles on that, and so far it's not sticking in my brain yet. If anybody knows how to generate Chebyshev polynomials for the intrinsic functions of the math library, do it and provide me code. That would be great. Otherwise, I'm going to have to learn it myself. You had a question?
Are there any instances for embedded that you wouldn't recommend using picolibc?
In instances for embedded that I wouldn't? No, of course not. Picolibc is the best. Probably on AVR processors, 8-bit AVR processors, where picolibc is so standards conformant that it's actually significantly larger than the AVRC library. The AVRC library still has, its math library is much less precise than even picolibc's. And so maybe you don't want to use it, but I use the AVRC library whenever I'm targeting those processors. Other than that, it's picolibc everywhere. I think that's enough questions for one day. Thank you so much.
Thank
for
you,
coming.
Keith.
Thank you.